Oh, already? Oh, wow.
Day of welcome back for the last day of our quantum Boltzmann machine workshop. We have two more sessions, lots of interesting talks so far. Happy to introduce Mingrui Jing for to lead us off for today. Please go ahead.
Thanks, Mark. Hi, everyone. My name is Mingrui Jing, and I'm currently a PhD student from Professor Xin Wang's group. And firstly, I want to thank that Professor Mark Wilde and Professor Xin Wang to organize such a great online workshop for QBM. Although my topic is not like about fully about quantum Boltzmann machine, but like it's a kind of like a new quantum machine learning model. So this is also the joint work with my friend Erdong Huang, Xiao Shi, and Professor Shenyu Zhang, and my supervisor. Okay. So firstly, here's the content of my presentation. So actually, can you see the black patterns suddenly appeared in my shared screen?
No,
Okay.
we just see your
Okay.
slide, and I thought at
Okay.
first
Okay.
that person might be Boltzmann, but I think it's Riemann, right?
Yeah.
Okay.
Yeah, because I just got something like because I'm the host of the Zoom meeting, so there's some crazy things happen. Okay. Anyway, so here's my content. Here's my content of the presentation. So at first, I will briefly introduce for those who are not familiar with quantum machine learning. I will briefly introduce the concept of quantum machine learning and particularly about what is quantum neural networks and the recent outcomes from the framework of dynamic Lie algebra. And in the second part, I will introduce our model, which is called quantum recurrent embedding neural networks, including the second framework. Um, and we will also discuss the application which we applied to solve using our model. And after that, I will deliver the main theory on why our model can avoid barren plateaus in some specific tasks. At last, I will showcase some of the interesting results of our model in symmetry-protected topological phase detection problem. Okay, so let's start. So quantum neural networks resemble the classical neural networks. We have some like data inputting vectors and processing hidden nodes and processing layers, and also the output layers. Quantum neural networks, also there's a lot of types of quantum neural networks, but in this talk or in this work, we focus on a special data re-uploading model, which we treat the quantum data as the quantum evolutions, and then we treat the whole network as a somehow like a quantum comp structure or parametrized quantum comp, and then we just run the whole model. At the end of the model, we will take some, of course, we will take some take some measurements to read out the processing result. And those results will be put into the classical post-processing method and to do something, for example, the discrimination task, Hamiltonian learning, and also in the condensed matter physics, some phase detection tasks. So you can see that there are a lot of applications which have been developed for quantum neural networks. And in particular, there's a very famous review in the previous year, 2 years ago, and which unified all the, or not unified, like collect all the important potential applications of quantum neural networks. For example, the enhanced quantum computing and the classical data analysis, also the quantum machine perception, and it can also be applied to the quantum simulation tasks. So here I provided some of the famous example of quantum neural networks that you might be familiar with. For example, the quantum convolutional neural networks, the quantum autoencoder, and also the recent one, which is called the quantum generative adversary networks. And during the development of quantum neural networks, several challenges has been also discovered. For example, the local minimal issue, and also the common thing like noise corruption issues for the whole network systems. And in this work, we try to give a kind of like a typical solver, like a message for kind of how we can avoid like Barron-Plato's challenge, which is actually the most famous challenge in this field. And luckily, 2 years before, almost 1 year before, there's a very famous framework called dynamic Lie algebra, which somehow unified the reasons for Barron-Plato's issues. So given the quantum neural networks expressed as a generator form or the periodic parameterized quantum circuit, the dynamic Lie algebra of this QNN is defined as a real span of a collection of all the generators and also closed under the Lie bracket. Likely in the finite case, such a real algebra can always be decomposed into simple ideals, and each ideals it can be seen as a subalgebra of the whole things. And you can see that the DLA contains very important information of this of the QNN, and in fact, this information drive or generate the whole system's evolution over time. So, based on the framework, several research have developed, and in particular, if a QNN is deep enough, by the assumption that form a unitary 2 design on the subgroup generated by this dynamic Lie algebra, then we can prove that with the trace form loss function, which is usually used in the variational quantum eigensolver, the expectation of the loss function with respect to any tunable parameter would vanish. And in particular, we can also prove that there's an explicit form of the variance of the gradient value, which is proportional to the inverse of the dynamic dimensions of each simple idea of this DRA. So you can see that the Lie algebraic theory of QNNs unifies the study of various sources of Barron-Plato's. So now we're standing at the crossroad of quantum neural networks, and there's a trade-off between expressivity of quantum neural networks and also the classical simulability. So on one hand, for those deep quantum neural networks, we may have high expressivity or the quantum advantages. However, it would probably encounter the Barron-Plato's issue, or it will be very hard to train. On the other hand, if we have structured QNNs, then it might have no Barron-Plato's issues, and also have the structured circuit, which are maybe efficiently to implement. However, those have been proved that maybe the tasks would be solved in classically like very efficient, or if we have like ambiguous quantum advantage. So how do you achieve this trade-off? There are several strategies which have been summarized for like literatures. For example, we should use localized states or the measurement, and we should usually also use the relatively simple quantum the circuit structures and circuit block. And in particular, there's one thing which has been emphasized by the recent famous Nature Communication paper. It says that we should use the algorithm structure, for example, the QSVT or the other very famous algorithms, which have been proven to be classically not simulatable. So now we are ready to introduce our quantum recurrent embedding neural networks. So firstly, here's the circuit framework of our model. And our model has like two registers. In the first register, we have m qubit, and in the second register, we have n qubit. We call the first register the data processing register, and the second one the data embedding register. And in this case, we focus on the quantum data, which usually being encoded in the Hamiltonians, which we denoted as the Hamiltonian bracket with the board X here. And those data will then be encoded via embedding map, which here we use the control evolution embedding into the entire network, so that the processing layer can, access the information of these data. And at the end of the model, we will do a local measurement on the processing register to read out the processed information. And those information will then be pushed in the classical processing method. For example, a very simple, like the threshold functions. And if we're assuming that these processing layers, which is colored in green, spans the whole unitary group, and we also make the assumption that the Hamiltonian encoder forms a commutative algebra, and we also assume that the m is in the scaling of logarithm of n. Then we can prove that the dynamic Lie algebra of this model can be easily decomposed into a very simple Dirac sum form, as shown here. And here the R represent the number of disjoint eigenspaces of this Hamiltonian encoder. And luckily, we can see that the control embedding, which we used in this model, makes the DLA a direct sum of simple Lie algebras. And we can also see that although this DLA has a very simple algebraic structure, however, to fully cover or to fully capture the dynamics of this model, we have to go through the entire eigenspaces of all the Hamiltonians, which is classically hard when the number of qubits in the data embedding register is large. So what can we do with this model? If you're familiar, so firstly, if you observe this model, you can find that it is naturally to think that if we choose a suitable measurement at the end, we can then use this model to solve quantum supervised learning tasks, and in particular to do some classifications on the Hamiltonians or the unitary evolutions. And luckily, we also have that the circuit contains the QSVT primitives. And in the most general cases, these Hamiltonians from the nature system and the many-body systems are generally not sparse, and which makes us to think that the quantum supervised learning task is a very good test task, because in this case that the decision function which we use to make the discrimination can always have like a high degree, usually have a very high degree. And this has been proven that for the QSVT primitives that to be like the PQP complete problems, even with that the M is taking the scaling of log n. And in this case, this model would so naturally contains these primitives. So we think that this task would be showing some advantages. And to do this task, let's assume that we have a data set, which is proposed on the left. We just need to encode this data into the Hamiltonian evolution, and then embedding the evolution into the system with a controlling evolution embedding. And to do this, we can use some recent development technique, for example, the implication of control evolutions through like shorter method. And then after that, we just do execute the whole model, do the measurement and processing to get the prediction values for each data. So for quantum supervised learning, let's just like have a very quick review. So in the usual case, we just run the whole model, and this as shown here that the whole circuit, if we represent as this unitary here, and usually we just use the mean square error loss function to complete the quantum supervised learning. However, this loss function is very hard to estimate on quantum devices. And we take the inspirations from quantum hypothesis testing. So here, if for a k-level discrimination problem, we just need to construct k different POVMs and then define the total loss function in the first moment of the trace form function, as shown in the below. Okay, so now everything is ready, and we can now present our main result on the trainability. So assuming that if we focus on the binary discrimination problem, we can fix our measurement to be on the right of the slides. And also we have made some assumption that to reach the max expressivity, we assume that the processing unitaries denoted as W here is sufficiently deep. And luckily we have some theorem that these QNNs, for those QNNs to achieve to design of the complexity group, we just need a polynomial number of slots. And in that case, we have random. If we use random initialization, we can achieve a fully mixed elements in the whole generated local compact group. So here's the main theory. So if we fix M in the scaling of log n, and we assume that the initial state for the data embedding register has sufficiently large overlap, and then we can conclude that the gradient of our total loss, the gradient variance of our total loss with respect to any tunable parameter can be lower bounded by the polynomial of n. So this theorem shows that our model can actually prevent from avoiding from encountering BP problem. And in particular, if we restrict the dimension of data processing register to be log n. And you might be interested about why we set up the sufficient large assumption. Well, intuitively, for this initial state, rho n, to serve as a good probe state, it must have a sufficient large interactions with these data Hamiltonians. So on the other hand, in many advanced quantum algorithm designs, especially for the QSVT-based algorithms, this overlap assumption is usually as a baseline to achieve some quantum advantages. So we take this form as a baseline for our model, which very interestingly, you'll find that this assumption also makes some interesting connection between the trainability of this network. Okay, now we also made some numerical tests for the trainability result. So the task is to classify whether a Hamiltonian is a Pauli or an involutory or a diagonal Hamiltonian. All the input stage would be the same as before, and we just input and embedded these Hamiltonians as the quantum data into the network. And we then just do the gradient sampling experiment. 500 random initial parameters of the model will be settled, and the rho n will be fixed. In particular, we fixed it to the plus state. And for each data set, we randomly test 50 Hamiltonians with the actual features from the diagonal, involutory, or the Pauli set, and another 50 random Hermitian matrices, which generated the higher unitaries. And here's our result. So as we can see, if we set m in the scaling of log n, the variance eventually like decayed, diverges from the exponential decay. So this proves the theory and numerically proves the trainability of our model. And then apart from classifying like Hamiltonians, we would also ask whether we can use our model to solve any other interesting quantum many-body tasks. And a very interesting and very important task is to do the symmetry-protected topological phase detection task. So as a start, I will give you a very simple model. So given a cluster Ising model here with periodic boundary condition, and in the previous literatures, we have known that this model would have a cluster state when lambda is less than 1, and will have an anti-Fermionic phase when lambda is greater than 1. So our question naturally becomes, can we detect these different symmetry-protected topological phases using our model? The answer is yes. So here we have tested this model. In the case one, we have set our model with 10 slots, and we take the processing layer with only 1 qubit and the data embedding layer with 8 qubit. And we have fixed the initial state to a very simple product state. And for the training session, we take 40 data, which is uniformly generated for sampling the lambda coefficient. And then we then test our model after training on 560 testing data. And here's our result. Actually, we can achieve like 98% accuracy at the end from the prediction. And we also have tested the effect from different data sets in the training set. Here we have shown cases in the right figure, which showcase that as the training size increases, we can find a slightly increasing in the performance at the end. However, there's also a very interesting point that at some stage that this model might have a decrease in the performance. Unfortunately, we do not know what happened at this stage, but I think we will figure it out. We do, and also we do more on like the SPT phase detection at the end. So that's the only one model, and we also test another model with like 2 parameters. So in this case, we have to fix the number of slots in a very large limit, and luckily we also have like we only need one. In this case, we only need one like a number of qubit in the data processing register. And in this case, we have tested n equals to 7, and n equals to 9 cases with some initialized designed state. And from these figures, we can show that so these gray dots are the raw data from trained model, and these blue dots are the actual classical processed data. And with these outcomes, we achieve 98% accuracy on like 200 testing data. Okay, so here's the conclusion. So recently we firstly introduced the recent development in quantum machine learning, including what is quantum neural networks and how the framework of dynamic algebra works for the Baron-Platus issues. And then at the end, in the second part, we introduce our quantum recurring embedding neural networks and from the inspirations to the QN design and how it can avoid Baron-Platus in quantum supervised learning tasks, and also the applications of our model in the SPT phase detection. Okay, so there's still some outlooks which we trying to solve in the future. So firstly, the control embedding is very hard to realize physically. So one point is to use some other maybe the practically friend embedding method and to test whether this is much better than the control embedding or to do some more quantum advantage tasks. And another one is to we need a more rigorous proof on the BQP completeness of this model. In particular, we need to show that, or apart from like the how this model can better encode the QSVT primitives. And there's also some other thoughts on the quantum recurring embedding neural networks. So whether we can treat it as like a very simple quantum neural and use it to build up some larger structures, and whether we can apply it to quantum sensing method problems, and whether we can develop some efficient warm start method on this initial probe state. And those are very important future directions, and we want to solve in the recent world. Okay, so that's the end of my presentation. Thanks.
Thanks a lot for your talk. I'll lead off with a question. So I recently saw your presentation at QTML, and
Yeah, yeah.
afterwards there were these points raised suggesting that maybe the model would be classically simulable. So I'm wondering
Yeah,
if you've thought about that since then. Um,
yeah, that's actually a like a very important question. So
mhm.
I think recently I was trying to figure it out. For example, let's see. Sorry, let me just put in these slides. Yeah, so here's the logic. I'm trying to find out that whether this model is classically hard to simulate. And I realized that because we're trying to use this model to solve quantum supervised learning, and it should depends on the decision function which we trying to approximate, right? And if this decision function for example, if we want to classify two different classes of set of Hamiltonians, if the decision function is very hard, for example, the degree of the polynomial that need to approximate decision functions is very high, then this model might need to then this function approximation problem is automatically a BQP complete problem. And in this case, our model would be like very hard to simulate classically. But yeah, I mean, this kind of logic, I'm not quite sure whether this logic is complete, but yeah. But
Okay,
that's really
that sounds
my
interesting.
thought. Yeah. And I have read some of the papers for the quantum classic, no, not like the quantum complexity theory.
Mhm.
And yeah, so to be honest, I'm very not good at the complexity theory, but I try to go through it.
Okay, sounds
Um,
interesting. Go ahead, Nana.
oh, so I don't have a technical question on this, but I'm just wondering, just from, a bigger picture point of view. So from what I understand, when you have this structure because, you want to avoid barren plateaus and things like that. But also, a lot of people are concerned about whether it's classically assimilable or not. But what
Yeah.
I'm wondering is, like, so what if it's classically assimilable? Like, if you can show that your particular structure, for example, is very well suited to classifying Hamiltonians, and this is a new, classical, like, could this be, an alternative classical architecture, like just for, data that is quantum in origin?
Oh, I think it depends on the data set. Like the dep
Of course it does. Yeah. So
yeah,
that's what I'm
yeah.
like, that's why it's not a, technical specific question. I'm just saying, just looking at it from a different point of view, instead of always asking about classical assimilability, can, are there, design principles for these architectures where you're making it more suitable just for quantum data, but you're still simulating it on classical machines?
Mm, yeah, that's a very good question. Actually, me and my supervisor trying to act this idea actually inspired from like the advanced algorithm design. So in our opinion, we think that to design like a potential quantum advantages neural networks, we might need to take inspiration from algorithms. So I know there's a bunch of like studies on like the complexity of solving classifying different datas of Hamiltonians, but in general, there's no good principles for designing the model. But I remember there's some of the literatures on like quantum kernel model, which showcases that for some of the data sets, the problem can dequantized. But yeah, s- s- I don't think there's a like a very general principle for designing these models. Yeah.
Oh yeah, but maybe we can leave it to the discussion session because we have some things recently that's, about kind of yeah, like for particular types of quantum problems.
Uh-huh.
Yeah. Uh but this is not for classification. This is yeah, but
Yeah, yeah, like
but I understand that Mark he is very on schedule and we are 2 minutes behind.
Yeah, indeed, we have the discussion session. Will you be able to stick around for that?
yeah.
What time is it?
It'll be
I
about an
remember
hour and a half from now.
I will try and stay awake for as long as possible.
Okay. Yeah. All right. So thanks again for the interesting talk. Our next speaker is Angela Capel, who's clapping right now with so thank you for joining us from Cambridge.
Thank you very much for the
And
invitation.
yeah, and she'll tell us more about, we've seen a number of interesting talks about thermal state preparation, and I think her talk will be in that direction. So
Yeah.
please go ahead.
Yes, thanks. So I hope that you're seeing the right screen.
Yes.
Okay, perfect. So thanks a lot for the invitation. It's great to be able to speak at this conference. Today I will talk about efficient preparation of the Gibbs state of the 2D toric code. And actually, well, there are many ways to do this, and here I want to focus in particular on two specific forms to do it. The first work that I will mention will have to do with preparation via dissipation, and this is in collaboration with all these people that I'm showing here. And the second work that I will mention has to do with preparation via dualities. So we will see that these two frameworks don't have to do, well, they are quite different from each other, but actually both of them produce very interesting results. So this is something that we will discuss towards the end. Let me start with the dissipation part. And before that, what I want to do is introduce the setting in which we are working in all these results that I will mention. So I will just consider finite range interactions in square lattices, so typical setting for this kind of problems. So what I will consider is square lattices like the one that I'm drawing here, and with a finite Hilbert space associated to each of the sides. So a global Hilbert space for the whole lattice given by just the tensor product of all the local Hilbert spaces. And I'm going to consider Hamiltonian that is local and is in particular finite range. So I'm going to assume that it is composed of patches like the ones that I'm drawing here. They can overlap, but they cannot be too large. So they can have different sizes like the one that I'm drawing here, but they cannot be too large. And the strength of all these patches is going to be uniformly bounded by a certain constant that we call the strength of the interaction. And on top of that, I'm going to assume during the whole talk that the Hamiltonians are going to be commuting. At some point, I will mention something different for non-commuting Hamiltonians, but this will just be to recall a result of another person. But for the results that I will present here, I'm always assuming that if two patches overlap, then the Hamiltonians associated, the interactions associated to these two patches always commute. And the main object that we will consider will be the Gibbs state, so the thermal state of the system at an inverse temperature beta that is larger than 0, which is given by this expression here. So I'm sure this has already been mentioned plenty of times. So this is the notation that I will use to denote that I'm working with the system lambda. Okay, so let me start with the formulation of the problem, and in a very schematic way, essentially what I'm doing is the following. I'm taking a local Hamiltonian, and I'm considering the Gibbs state of that Hamiltonian. Now you see that if there's no confusion, then I will just omit the lambda parameter, the lambda superscript from rho, just to not charge notation too much. And essentially, I'm considering that there's a Gibbs sampler. So for the moment, I'm not talking about which specific form this has. And this is just a machine, whatever it is, such that it takes any initial state, so any initial density matrix, we insert it into this Gibbs sampler, and it outputs something that is very close to our Gibbs state. So it's not going to be exactly the same. It's going to be this rho tilde, but rho tilde is going to be at a distance smaller than epsilon from the Gibbs state. Okay, so this is essentially what we want to do in this task. And now the question is essentially, how do we do this? So how do we do Gibbs sampling? And that means, what is this green box that I drew here? Well, I already kind of spoiled it in the first slide. A canonical way to do Gibbs sampling is following dissipation, so using dissipation, and this is what we will talk about in the first part. And this is based on this paper, in which I'm talking about modified logarithmics of Levin inequalities, so we will see in a moment what this is. So essentially, when I'm talking about dissipation, what I mean is the following. We have a system, like the one that I was describing before, a square lattice like this, and now this is contained in an environment, and this is weakly coupling with the environment. So that means that the energy of the system is going to tend to dissipate with time. And in particular, since I'm assuming that there's weak coupling, if I make some further assumptions that I don't want to discuss in much detail here, but in particular they have to do with the memory of the environment. So if the environment in the future doesn't see what happened in the past, only sees what happened in the present, then we can assume that there's Markovianity. There's something that is called a Markovianity approximation. And that means that the continuous time evolution of any initial state in the system is given by something that is called a quantum Markov semigroup. I don't want to go into the technical details of what this means, but essentially, if we have a system that is nice enough, so if now our environment is a thermal bath that satisfies certain properties, what this means is that there is an object that is called a Lindbladian that describes the dynamics of the system with the time. And what it satisfies in particular is that when we apply to rho, this vanishes. So rho is what we, in an abuse of notation, say a fixed point of L, or what is the same, rho is a state in the kernel of L. Actually, it's the only state for which this is satisfied. And what this automatically implies is that if we consider this object that I was mentioning before, this quantum Markov semigroup, this is nothing but these elements that I'm writing here, this e to the TL. Then if we apply all these elements to any initial state sigma, and now we let our time evolve to infinity, we are always going to have convergence to rho. So essentially what this means is that our system, doesn't matter how we initialize it, our system is always going to thermalize to the thermal state. So it's always going to converge to the thermal state. That is going to be rho. And this is the basis of dissipation. And this is something that is crucial for many applications, and in particular is crucial for this field of dissipative quantum state engineering, because this provides a robust way of engineering some states and algorithms. And the idea is essentially that, well, it doesn't matter how you initialize your system, right? So no matter how you do that, if you wait for a large enough time, you're going to be close enough to your Gibbs state. And even these kind of systems are typically robust against noise. So if you add some perturbation here that models a certain kind of noise, you still have convergence to something that is very close to the Gibbs state. Which means that, okay, you can actually engineer a lot of things from this theoretical idea. But of course, we cannot wait for an infinite time, right? So it's very nice that we have guaranteed convergence in an infinite time to the Gibbs state, but what we actually want is that after a short time, we are already close enough to the Gibbs state. It doesn't need to be exactly on the Gibbs state itself, but we are okay if this is close enough. And by close enough, I essentially mean that, well, after a certain small short time t, this quantity minus the Gibbs state, that the one distance of between them is smaller than a certain parameter epsilon. So the question is, when do we have this? And there are two ingredients that we have to look at here. The first one of them is that if we are actually trying to do this in a computer, in order to be able to prove an inequality like this in the computer, what we have to look at is, first of all, that this can be efficiently implemented. So we need that the quantum Markov semigroup itself is something that can be efficiently implemented in the computer. So, and that means that the Lindbladian has to be efficiently implemented. But the second ingredient that we need is actually that this object is close enough to rho after this short time that I'm mentioning. And that means that the evolution has to quickly mix towards this Gibbs state. And this is in the regime of the so-called rapid mixing or fast mixing, which are two different things. I don't work a lot on the part of the efficient implementation of the Lindbladian, but I rather work on the second part, on the rapid or fast mixing of the evolution. So the first thing that I want to mention about the first part, the part of the implementation of the Lindbladians, is that there are a few works in this direction, both for commuting Hamiltonians and for non-commuting Hamiltonians. For commuting Hamiltonians, people typically use the Davis generator because of the tradition from the mathematical physics community. And for this object, what is known is that if the number of qubits where you are considering, the number of qubits that you're considering in your system is of cardinality of lambda, then the circuit complexity that is necessary to efficiently implement the Davis generator is the one that I'm writing here, is of order lambda squared polylog of lambda, and the circuit depth is actually of order lambda polylog of lambda. This is based on the best results in this direction that are known for the implementation of the Davis generator. However, in the non-commuting case, this has been a complicated question for many years because the Davis generator, if we try to use it for a non-commuting Hamiltonian, we actually see that the object that we obtain is non-local. And that means that for implementation, it was quite complicated for a while. So recently, this new operator appeared, this CKG generator, which is named after the three authors that introduced it. And what they showed is that this object is actually efficiently implementable in the sense that it can even be implemented with the same circuit complexity and the same circuit depth as the Davis generator. And even though it's not local, it's quasi-local, so it behaves in a pretty well way. So it's something that is it's very nice, and the efficient implementation part of the Lindbladian is pretty much settled with all these results. So now the question that we are interested in is more related to the second part, to this quick convergence to the Gibbs state of the evolution. And this is something that is typically explored in the field using some kind of inequalities, for example, like this modified logarithmic Sobolev inequalities, which are inequalities of this form. So essentially, you have the relative entropy between an evolved state and an equilibrium. And if this is upper bounded by the relative entropy between the original state and the Gibbs state with an exponential decay rate, then we say that we have this kind of inequality. And this automatically implies this bound that I'm writing here, which essentially says that if we take now, here rho and sigma reversed. So if we take here the evolution of an initial state, sigma should be, and take the distance to rho, then we see that the one norm of that difference is upper bounded by something that scales polynomially with the system size and decreases exponentially with time. This is what is called rapid mixing. And this is equivalent to say that something that is the mixing time of the evolution is something that scales polylogarithmically with the system size. And this is as good as it can get for this kind of evolutions. So what we can see is that even if we assume that we have a Hamiltonian that is a single-side interaction, so essentially the qubits don't talk to each other, or the spins don't talk to each other, and we have a Lindbladian that behaves exactly the same in the same way, we already have here a linear factor. So you cannot do better than polynomial. So this is essentially as good as it can get. And this is something that is typically difficult to prove, but is what you really try to achieve. And there are many other ways to find bounds for these quantities that don't have anything to do with the modified logarithmic Sobolev inequality. One of them is, for example, using the spectral gap of the Lindbladian. So if the Lindbladian has a positive spectral gap, then we get a bound of the same form, with the only difference that here you actually have an exponential prefactor on the system size. Or what is the same, you have a mixing time that scales polynomially on the system size. So that means that this bound is actually exponentially worse than the one that you have here, but it's typically much easier to prove because, well, proving spectral gaps of Lindbladians is much easier than finding these kind of inequalities. But anyway, the reason why I want to mention these two things is because from the point of view of Gibbs sampling, actually both of them are equally fine, because what we are only caring about is having an algorithm that is polynomial on the system size, and this is something that is obtained by using both of these kinds of bounds. Because if you have rapid mixing or if you have fast mixing, what happens is that the mixing time, as I was saying before, is either of polylog of the system size for rapid mixing or of order lambda log of lambda for fast mixing. And now for all these systems that I'm writing here, we already know that there's either rapid mixing or fast mixing. So these are the typical systems that you could imagine that should behave well with respect to Gibbs sampling. In the commuting case, I'm talking about 1D translation invariant systems at any positive temperature, and also in any other dimension. I'm talking about two local interactions, nearest neighbor interactions, assuming that there's decay of correlations and there's a gap that can be actually lifted to rapid mixing. And if we talk about some specific models, then if we talk about quantum double models, for example, what was known before this work was only fast mixing, not rapid mixing was, rapid mixing was unknown. So this is actually what we did in what I'm just about to present. And in the non-commuting case, what you know is that for any dimension at high enough temperature, there's always rapid mixing for the Chen Lindbladian, so for the CKG Lindbladian that I was mentioning before. So this is pretty much the state of the art of this part of the presentation. And so now to recap what I was describing before, we are looking for the situation in which we have that this norm is bounded by epsilon, so this is small enough. And we were looking for these two ingredients, the efficient implementation of the Lindbladian and the rapid fast mixing of the evolution. And in the first case, we had a circuit depth of lambda polylog of lambda. And for the rapid fast mixing, we actually had these orders of the circuit depth as well. So that means that if we put all of them together, the worst case that we can have having fast mixing, for example, is a circuit depth of at most for the lambda square polylog of lambda, which is pretty good because it's polynomial in the system size, but it's actually polynomial with a low degree, right? So this is something that is considered to be pretty efficient to prepare Gibbs states. So now the question is, can we extend this approach to more systems than the one that I was mentioning in the previous slide? And in particular, can we prove rapid mixing for the 2D toric code and similar models? And the answer is yes. So before showing the result, let me recall what the toric code is. And the toric code is essentially the object that I'm drawing here. So we have a square lattice in which now we are placing the spins in the middle of the edges, not on the vertices anymore. And we have periodic boundary conditions in both directions. So here this side is reflected to this, and here this side is reflected to this. So this is really like a torus. This is like a donut. All the interactions that we have in the Hamiltonian that we define over this geometry are either star interactions, which are of this form, or plaquette interactions, which are of this form. So a plaquette interaction, which is this blue thing that I'm drawing here, essentially has 4 Pauli sets. And a star interaction, which is this star that I'm drawing here, has 4 Pauli axes. And now the Hamiltonian is going to be just the sum of all these plaquettes and all these stars in all the possible sides of the lattice. So this is something that is a very typical model that was initially introduced with the purpose of doing error correction. But now there are many other models that are called CSS models, CSS codes, which are related to it and with a bit more general geometry and a bit more general properties. So one of them is something that is called the rotating surface code, which is something like what I'm drawing here. So we have a bunch of squares. This is like a checkboard. These blue squares are going to have set in the 4 squares, in the 4 vertices, sorry, and the yellow, orange tiles are going to have x in the 4 vertices. And another model that is pretty well explored in this direction is something that is called the 3D toric code. So it's essentially an extension of the 2D toric code, but to one more dimension. And this is something that is, well, formed as well by plaquettes and stars. Now the plaquettes are more or less the same, but they go in the 3 directions of the 3 dimensions. And the stars just have 3 dimensions directly, so they are stars in 3D. And then you have other objects like tessellations, like the one that I'm drawing here. So for all these models, we can explore these modified logarithmic of Levin inequalities that I was mentioning before. And then what we could show was that the Davis-Limbladian, so the Davis generator that I was mentioning before, for the 2D toric code has rapid mixing at every positive temperature. And in particular, if we look at the 3D toric code, and this is something that was totally unknown before, it's like what happens now is that you can study the stars separated from the plaquettes, and you can see that the Hamiltonian part, so the Limbladian part associated to this Hamiltonian part of the model, is going to converge very quickly to the corresponding Gibbs state, but this part is going to be much slower, and that means that half of the Davis-Limbladian is going to have rapid mixing and the other half not. In the sense that at high enough temperature, both of them are going to have rapid mixing, but at every positive temperature, only half of it. But this is still enough to say that quantum information that is stored in the 3D toric code is destroyed exponentially fast, and only classical information can survive long times. So this is a pretty interesting finding, in my opinion, related to this model. But coming back to preparation of Gibbs states, what this means is that now for these models, we also have this order of a circuit depth to prepare the Gibbs state. However, there's a problem here, which is that this depends on the mixing time of the evolution, and the mixing time depends exponentially on beta. So even if this is pretty efficient with respect to the system size, it's pretty bad with respect to the temperature, because now if you take the temperature very close to 0, this is going to be very large. So the question is, can we find another approach that we can use for these models that is more efficient for very low temperatures? And this is what we did in this second paper that is done via dualities. And now here, the math behind it is actually much simpler. The idea is very straightforward. It's essentially the following. So we consider 2 Hamiltonians, H1 and H2, and we say that they are polydepth dual if we can map one to the other by using a unitary that can be implemented by a circuit of polynomial depth, and a circuit of 2 local gates. And that means that now if we consider the Gibbs states associated to one Hamiltonian and the other Hamiltonian, then they also have the same relation. So it's pretty easy to check this, no? That now one Gibbs state is related to the other one just by conjugating by these same unitaries that are of polydepth. So now this automatically tells us the following. If one of them can be efficiently sampled, the other one as well, because we are limiting this U to have polynomial depth, not more than that. So in particular, in a schematic way, if rho 1 can be efficiently sampled with something that we call C, whatever it is, with a circuit that we cannot see, then rho 2 can be efficiently sampled just by composing with this unitary that I'm saying. And now this is going to be polynomial, this is going to be polynomial, so the whole circuit to sample rho 2 is also going to be polynomial on the system size. This is the idea behind this project. But then, of course, we again have to look for 2 ingredients to prepare a relevant Hamiltonian H2 that we are interested in. One of them is to find a polydepth circuit that maps it to H1. And the other one is to find an efficient sampler for rho 1, which is the Gibbs state associated to H1. So I'm going to skip this example in the interest of time, and I'm just going to go to the results directly. So again, we are focusing on the 2D toric code that I was mentioning before. And what is happening here is that now we can actually see that if we take all the stars, which are these pink interactions that I'm drawing here, and all the plaquettes, which are these blue interactions that I'm drawing here, then what we can actually prove is that you can separate the stars interactions from the plaquette interactions, and you can prove that for the 2D toric code in an L times L lattice, there exists a quantum circuit C that is composed only of CX gates and Hadamard gates, and actually not a lot of them, such that if we take now the plaquette part and conjugate it with the circuit, and if we take the star part, and if we take the plaquette part and conjugate it with the same circuit, what we obtain is actually 2 disjoint 1Ds in chains. So just in a visual way, so that it's easier to see what I'm saying here, we start with these pink interactions and with these blue interactions, and we end up with these 2 snakes that are drawn here. So you see that now the interactions don't overlap anymore because the spins where they are defined are totally disjoint. And actually we have 2 spins here where nothing is happening. And the depth of the circuit that we are using to go from here to here is actually pretty short. So it's something of order n to the 3/2. So it's something that is pretty short. And the consequence of this is essentially that the ground and the Gibbs state of the 2D toric code can be prepared with a gate complexity that is quite small, so it's of order L3, L being the size, so also of order n to the 3/2. And now this is for any temperature, for any positive temperature between 0 and infinity. And of course, we don't see the temperature at all in the algorithm that we are using to bring the initial 2D toric code to this coupling of these two 1Ds in chains. So, okay. Let me just briefly mention that this is something that can be extended to many other models that are called CSS codes, as I was saying before. And in particular, these models are composed of sums of Pauli strings. So each HI that I'm writing here is a Pauli string, it's a string of Paulis, and they are all mutually orthogonal, so they mutually commute, all of them. And when we have these kind of models, what was shown in these papers is that all the terms can be simultaneously diagonalized with a quantum circuit that is of quadratic depth, so something that is very short. And this is crucially what we are using in our proof, because now we know that whenever we have a Hamiltonian of this form, all the terms are polydepth dual to classical Hamiltonians because they are diagonalized, right? So being diagonalized means essentially that they can be mapped to classical Hamiltonians. And then the question that you have is to which classical Hamiltonians are they being mapped? And well, in the case of the 2D code, the 2D toric code, it's kind of easy to see that this is mapped to 2 1Ds in chains. We have a collection of models for which we can do something similar, and this is mapped always to either collections of Is in chains or non-interacting single spin Hamiltonians, which are even easier, right? Because it's just Hamiltonians where all the sides don't talk to each other. So that means that they are much easier to sample. You just sample everything at the same time. And I have here a list of all of these, but since I already have to finish the talk, I think I will leave for later for the discussion the analysis of these models if anybody's interested. So let me just conclude by comparing the 2 results that I just presented here and just saying that, well, if you want to prepare Gibbs states of models, here I just gave you like 2 different tools that can be used. Dissipation and dualities, and in particular, if you look at the case of the 2D toric code, we see that the circuit complexity of, via dissipation is a little bit more than in the case of via duality, and also it depends exponentially on beta, and here we have no dependence on beta whatsoever, so in that sense, the circuit complexity is better in the case using dualities, but the circuit depth is actually better via dissipation, and here the circuit depth, we have no idea. We can only look at the complexity, but we don't really know if we can do things in parallel or not. So in principle, this might be worse. And via dissipation, you have other consequences such as loss of information. In both cases, we actually think that this is applicable when we actually see that this is applicable to many other models. The main difference with respect to the proofs is that the proofs via dissipation are much harder mathematically, and here these are like much simpler because you saw that the only thing that we're actually using is that two Hamiltonians are dual, so it's really very simple. And this is, of course, something that sets the basis to possible extensions to other Lindbladians and non-commutative Hamiltonians, and this sets the basis to possible extensions to higher dimensional Paulis, for example, non-commutative Pauli strings, and some other things of this form. So this is everything that I wanted to tell you about today, and thanks a lot for your attention.
Thanks a lot for a very interesting and informative talk. I'll start out. So at the end, you're talking about possible extensions to non-commutative Pauli strings. That would be of very high interest. Do you have any further comments about that? Or is that
So
Go
not
ahead,
yet. I
sorry.
mean, that's something that we want to explore, and I've already talked to a few people that are actually like super interested in this. The procedure that we are following in this paper doesn't automatically apply because we are using strongly this result that I mentioned very briefly from Teme and Van der Berg, where they are diagonalizing things essentially in a quadratic depth. And of course, in the case of non-commutative Pauli strings, this is not going to work at all. So the method that they use for that doesn't work in this case. So we would have to find an alternative for that part of the proof. The rest of the proof could follow, but that part could be difficult.
Could you clarify the contribution of the Teme et al. Paper?
Yeah.
Yeah.
So they have this result that says that now if you have a Hamiltonian of this form, and now all the HIs are Pauli strings, and they mutually commute, then they can be simultaneously diagonalized, and the quantum circuit that you require for that is of quadratic depth. And
Okay.
this is something, the way to prove it is using tableaus. So it's essentially writing the interactions in tableau like this. And then this part corresponds to the X interactions, and this part corresponds to the Z interactions. And then they want to make these zeros. And by making these zeros, then they see how much they are changing the Z interactions, because of course, once you have only Pauli sets, you're already classical. And they see that you can actually do this with CX gates, Hadamard, and phase gates in an order of n squared depth. So it's pretty nice, and this is something that we are importing from their work to what we are doing here. But of course, we will have to find an alternative for this, for the non-commuting case.
Okay. That sounds good. So you didn't really comment about so it was a very nice overview of everything, but to get a modified logarithmic Sobolev inequality, that seemed to be a core ingredient, and you kind of glossed over that.
Yeah.
I think you said that it's challenging mathematically to establish those. Can you comment a bit more about how one would approach such a
Yes.
problem?
No, that's a very nice question. That's proving a modified logarithmic Sobolev inequality is proving an inequality like this. And well, as I said, this is very difficult in general, but what we realized for these models is that if you take the Gibbs state of the toric code or any of these CSS codes, this actually splits between the plaquette part and the star part. And once you are at the level of the plaquette part or the star part, the Lindbladians also split between the plaquette part and the star part. So that means that if you look at each of these parts separately, you still have a quantum process, because now you are evolving any quantum initial state, but the Gibbs state that you are putting here, which is either the plaquette or the star part, is already classical, because these two parts separately correspond to two classical 1D Ising chains. So that means that, even if this is still a quantum problem, it's a bit easier to deal with. And one thing that we have been working on for many years is to relate these kind of inequalities to the decay of correlations on the Gibbs state towards which you are converging. And what we saw in this paper that I was presenting here is actually that if you only look at the decay of correlations on the Gibbs state, the same thing happens. It splits between the star part and the plaquette part. And that means that now you only have to prove decay of correlations classically. So you have that classically, decay of correlations on the star part, for example, implies a Log-Sobolev inequality for the Lindbladian of the star part, and the same thing for the plaquette part. And once you have a Log-Sobolev inequality for both parts, you can put them together, so to say. And this is how you obtain the Log-Sobolev inequality for the whole thing. So this is why for these models, this works pretty well, even if in general it's much more challenging.
Nice.
So I don't know if this makes sense.
It does. Yeah.
Yeah.
I'll ask you more questions about your talk. Will you be able to stick around for the
Yeah.
discussion session? Okay, that's really great. Are there other questions for Ángela?
I just have a, more general question about, these Gibbs state preparation through dissipation. So when if you want to prepare Gibbs states of, say, different temperatures, right? Where does
Yes.
that come in? Do you just like factor the temperature like into the norm, the Hamiltonian, or what's the
Yeah, that's pretty much what I was doing here. Yes, I was kind of putting it inside the Hamiltonian itself.
okay. Like is there another way to do this? Like because yeah, like if you want to use a mixing method and then say you want to start to cool the system in some way, like can you still use this kind of dissipative dynamics to do that?
That's a very good question. I guess it would depend on the system and on whether you can keep these properties surviving when you take temperature like to zero or to a low temperature or something like that. Because what typically happens in systems beyond 1D is that very often you have rapid mixing at high temperature but not at low temperature. So if
Yes, yeah.
you really require one of these properties, either rapid or fast mixing, you're probably going to have problems starting with this. I mean, for the preparation of the Gibbs state, starting from the fact that this doesn't mix fast enough. So this is either going to be seen from the fact that at some point some norm will explode because of what you are saying, because of inserting the temperature inside, or
Yeah.
just because you're not going to approach the state quickly enough, even if the implementation of the Lindbladian is okay. But I think it depends on each model, So for some models, it might actually work fine.
Okay, cool.
Yeah, thanks.
Thank you.
All right. I guess there are no other questions, so we'll reserve more for the discussion session
Great.
and move on to the next speaker.
Oh,
Okay,
right. I
good.
have to.
So I'll chair you, Nana. Okay.
Oh, okay. All
So
right.
yeah. So now our next
I'll-
speaker is Nana Liu. She is a associate professor and PI at Shanghai Jiao-Tong University. Her research focuses on employing quantum resource for both quantum computation, sensing, and she recently has many nice works on kind of Schrödingerization, like quantum simulation for solving PDE. That's amazing. And today we are very happy to have Nana talking here. Yeah, it's your stage.
Thanks so much, Shiwan. Yeah, so and thanks so much for the invitation. I'm going to talk about something that we do with Mark actually. So I thought Mark was going to introduce me. So I'm Nana. I'm in Shanghai. Yeah, and today I'm going to talk about something that I've learned, through working with Mark on the importance of quantum Boltzmann machines when we consider its relevance to optimization as well as quantum thermodynamics. Let's see. Yeah, so this work is all thanks to these guys. So the great work from Mark, Michele, and Dhrumil. And yeah, so I just feel really privileged to have been, a part of this. I've been learning about quantum Boltzmann machines from Mark and his group. And I've, always been interested in quantum thermodynamics. That's actually one of my first papers was on quantum thermodynamics. So it's been a real privilege to actually learn from these guys and, learn about this topic. So this whole conference is about, Boltzmann machines and, both classical and, well, most forms of quantum Boltzmann machines that we've seen, it has a form that looks like this, right? Where mu is some, tunable parameter and our h bar Hamiltonian is linear in this mu. And you say, okay, all right. And, it looks very much like a Gibbs state. So which is what, Ángela's talk is all about, how to prepare these states. And indeed, if we look in, classical thermodynamics. If we take a very important example where, suppose we have a mu, which is a constant, it's a parameter, then we have a form of a Gibbs state that looks, exactly has a form, what we call a grand canonical ensemble. And this is an ensemble, unlike the microcanonical ensemble that, we hear about in classical thermodynamics, where just energy is conserved. In this case, you have your subsystem, with a reservoir, and then you're saying that there are actually other quantities which are conserved. So typically, if you're learning classical thermodynamics, it would, a conserved quantity would be like particle number. So you allow particles to float in and out between your system and your reservoir, but as a whole, that particle number is conserved. Okay, and then your thermodynamical ensemble looks like this. Now, and what puzzles me is that, I searched through the abstract book of this conference, and despite the fact, of the very close similarity between these states in equilibrium, okay, so grand canonical ensembles with Boltzmann machines, I haven't seen any other mention of the word thermodynamics. I've seen quite a few, mentions of Gibbs states and thermal states, like in Ángela's talk, but nowhere else, do people actually mention thermodynamics. But, from here, we actually see just from the form, it's quite obvious that somehow, these things are very deeply related. And we want to ask, like, firstly, can we utilize, okay, intuition, from what we learned of thermodynamics, in physics, and how that would inform us on, how we might be able to use things like Boltzmann machines and quantum Boltzmann machines to solve certain problems. Okay, so one thing, from thermodynamics that we know of, is that a thermal state is a minimizer of free energy. Okay, so because why is it that physical systems, if you're in a system with a reservoir and you have interactions, okay, just like in Anna's talk before, when you set up coupling between system and the reservoir, and after sometimes a short period of time you can actually thermalize, okay, because physical systems prefer to stay in this state because it's actually a minimizer of free energy. And similarly, when we think about quantum thermodynamics now, the difference, okay, between quantum thermodynamics and classical thermodynamics is that now that while you could have quantities which are conserved, okay, as a whole, okay, between your subsystem and your reservoir together, but the actual quantities themselves, your Q's quantities, they themselves don't have to commute. Oh, sorry, it's supposed to be Qi and Qj. It's a typo there. The Q's themselves do not actually have to commute with each other. Okay, and this form is called non-abelian thermal states of thermodynamical systems, where you have conserved non-commuting charges. So I'm sorry, this actually is equal to 0, but the Q's themselves no longer commute with each other. Okay, so this is unlike the case in classical thermodynamics, where you could have particle number of different species, and you can, of course, particle number of species A and species B, those observables, they commute with each other. But if you now go into quantum thermodynamics, you have quantity like spin, then we know famously, of course, that these quantities don't commute with each other. And then in quantum thermodynamics also, then we can observe that these states is also a minimizer of free energy. Okay, and this actually suggests to us if it's a minimizer of some quantity, then this becomes a natural ansatz to solve an optimization problem. Because what do we do in optimization? We're always trying to find a solution, like to minimize, okay, or maximize, okay, some quantity, okay, some loss function. Okay, so this suggests to us that, the thermal state, which is a natural result of dissipative dynamics, okay, can be a natural ansatz. And we actually see this form is actually also the form of a quantum Boltzmann machine. Okay, so this is how these topics are connected. So what type of optimization problems would be interested in? Well, one is actually semi-definite optimization. And of course, there are many broad applications of semi-definite optimization, so in quantum physics, machine learning, control theory and systems engineering, signal processing, inference problems, and so on. And what is special about semi-definite optimization is that not only are we optimizing, okay, some quantity, but it's optimization subject to a constraint, okay? And this constraint you can think about as a conservation constraint. So, and that should remind us of, things like in thermodynamical systems, like in the grand canonical ensemble, you're not only minimizing free energy, but you're minimizing a subject to you, for example, conserving particle number. Okay, so the formal statement of semi-definite optimization is that if you're given, say a D by D Hermitian matrices C and A, subscript I, then you want to minimize the expectation value of C and X, where X is positive semi-definite matrix, such that the observable of X, you can think about the trace of AI of X, that is some constant, okay, value. And here we want to transform this, into a more quantum, okay, looking problem where, we want to minimize the expectation, by selecting the appropriate X. But if we're doing this, whenever we think about quantum, systems, then we want to work with things like density matrices. Okay, so in general, X is not a density matrix. However, if we, make the assumption that, its trace is bounded, then of course we can always turn this into an optimization problem where we're optimizing or where we're optimizing on the trace of, some Hamiltonian on rho, where now this H is simply, the original Hermitian matrix C, okay, but then you're, adding a qubit, okay, and then subject to the conservation of the observable of Q of I on rho, where your rho is now a density matrix, okay, it's a trace one, okay, Hermitian matrix. So we're just now turning this into a more quantum-looking problem. But what is a quantum thermodynamical system? So with a quantum thermodynamical system, we're given, Hamiltonian H, but we're also given a collection of what we call charges. Okay, so you can think about this as, particle number or spin or angular momentum operators as you like. So, Q1 to QC, and they're all, D by D Hermitian matrices. And this describes a thermodynamical system where, we have this Hamiltonian H, but the Qs themselves, they actually don't commute, okay, with each other. Okay, this is the quantum part of quantum thermodynamics. And in these systems, we can have an energy minimization problem subject to the constraint that we have conserved charges. Okay, so energy minimization means that we want to find the density matrix such that the Hamiltonian, okay, is minimized subject to the expectation value of Q, okay, of Q of I, capital Q of I, okay, is equal to some constant, little Q of I. Okay, so then, from this form, we actually see that the energy minimization problem in quantum thermodynamics is equivalent to semi-definite optimization, okay, in the way that we saw previously. Okay, so we're not quite there yet in thermodynamics, because in thermodynamics, we care about free energy rather than energy. So let's see how energy is related to free energy minimization. Now, because real physical systems, they operate in finite temperature, so then, free energy, as we, minimization is much more natural, okay? And free energy is basically just energy minimization, but you have to include the effective temperature, so then it's expectation value of H minus temperature, T multiplied by S, where S is the von Neumann entropy. Okay, so we see it's almost there, but except with the T, but we see that if, temperature is very low, okay, then free energy minimization is basically like energy minimization. Okay, so, we can take a band of our Neumann entropy. Of course, we can always improve upon this band, okay, if if we know certain structure about rho, if we have more information about it, but this is just, like a fairly crude, but still good enough band. And then here we see that then, of course, we can see in the zero temperature limit, free energy minimization is equivalent to energy minimization. And if we want the final result to have some error epsilon, okay, in our energy, then, simply, having temperature scaling as epsilon on log D, okay, and if, or D is the dimension of our system, okay, so this is 2 to the power of n, okay, a number of qubits. So basically T scaling with epsilon on n. Okay, so that's a sufficiently low temperature, okay, for us to have the equivalence between energy minimization and free energy minimization. And of course, as we know, the solution for free energy minimization will take the form of a thermal, okay, a quantum thermal state. Okay, but now we'll just see it a little bit more formally. And here we see that free energy minimization, subject to constraints, okay, is really the same problem as if we were to maximize a particular function of the chemical potential. So, the mu, the tunable, parameter mu that we saw before in Boltzmann machines, that actually corresponds to a chemical potential, okay, in a thermodynamical state. So let's have a look at this. So the first line, I mean, this is just the statement, okay, of free energy minimization subject to constraint. And of course, to deal with constraints, we just make this Lagrange multiplier problem. Okay, we take the supremum outside, and here we can apply the minimax theorem, so we can interchange between the mim and the supremum. Okay, and then we get a quantity, okay, here. So mu here is interpreted as a chemical potential, and Q of I, these are our conserved, the values of our conserved charges. Okay. And then so if we look on the left, okay, after some algebra, okay, then we're actually able to rewrite our term, okay, in terms of the quantum, relative entropy quantity, where rho of T, okay, if you recall on the right, rho of T actually is a form of the quantum thermal state, okay, the thermodynamical state where your Q of I's don't need to commute with each other, okay, and your Z of T is your partition function. So what we know, okay, from quantum relative entropies or any of the entropies is that it's positive, okay, and it's only zero, okay, because it takes its minimum value when rho is equal to rho of T. Okay, and of course this just formalizes what we expected, which is that the state that minimizes, okay, free energy, I mean, that should take the form of a quantum thermal state. And here we see that indeed, rho of T, the quantum thermal state, is the minimizer. But let's have a look also at the result, which is that the result of this minimization problem then becomes a function only on mu, because mu is now the only undetermined parameter. Because we know what rho is now, it's a thermal state, but the thing that needs to be determined is mu, okay, the chemical potential. And this is a function that we want to solve for. Okay, so now free energy minimization subject to constraint becomes a minimization or maximization problem with respect to the chemical potential mu. Okay, so now these two problems are equivalent. And it becomes a much simpler problem because, instead of trying to determine a state, all we need to do is trying to determine the value of a parameter. Okay. Yeah, so then so what this says is that if we're able to determine what mu is, right, by maximizing the function, okay, f of mu, okay, which is mu dot q minus t log z, then, to realize, this kind of algorithm, then we just need to prepare our state in the form of rho of T. So using, Ángela's, algorithm or, anyone's algorithm for preparing these kind of thermal states. And then we tune mu so that it maximizes this function f of mu. Okay, so, and then that allows us to solve, again, our semi-definite optimization problem. Okay, so how do we actually do this optimization? How do we actually find this appropriate mu? Well, it actually turns out that this will give us actually unique mu. Okay, so here this is the objective function, f of mu, and then we have the gradient, okay, of this, and this, is well known from those who do training, okay, in quantum Boltzmann machines. Okay, it's just the first. The gradient is Q of I, okay, the constant value minus the expected value for your particular rho of T, okay, at your particular mu. But if we look at the second derivative, okay, so that the elements of your Hessian function, okay, of your Hessian matrix of f of mu, this is minus I of the Kubo-Mori information matrix, and I'm sure Dhrumil after this will tell you much more, okay, about this matrix. But the only thing that we need to know about it is that the Kubo-Mori information matrix is always positive, okay, semi-definite, and then this f of mu is then concave in mu, so which means that we can maximize this f of mu globally. Okay, and we can do this by, gradient ascent. Okay, it's not descent, but because we want to find the maximum value. Okay, so, there are no sort of hidden local minima anywhere. This is actually a very well-behaved function where, these gradient optimization methods, they can work very well. Okay, so the overview, okay, of the idea is that, you start with your energy minimization problem, okay, and you add a temperature, okay, T, okay, so it becomes a free energy minimization problem. And we see that the solution to this, okay, well, it's dual to the problem, it's equivalent to the problem of finding, the appropriate chemical potential mu, which maximizes, okay, this function, okay, which is mu dot q minus T log Z. Then to actually solve for this problem, we can actually use gradient ascent. And then by setting the temperature to, scaling as epsilon on n, then where n is the number of qubits, then this would be able to, approximate the solution of the original energy minimization problem, which we saw is actually equivalent to the semi-definite optimization problem. So a little bit more detail on the actual algorithm. So so here we see, well, it's actually pretty straightforward because we know the gradient, okay, of f of mu, and this is just a little q. So this is the constant, conserved quantity q minus the expected value of the charge of your thermal state at the particular mu, okay, in the particular time step that you're in. And we can interpret, this gradient step, which is, in the red box on the left. We can interpret this in a thermodynamical way. So suppose you started off with, you have your system and your reservoir, okay, and the state of your system is the thermal state. Now, at any point where if you were to measure the actual charge, of your system, and you find that the charge of your actual system is actually less, okay, than what you expect, which is, Q, the conserved quantity. So then how does the system actually respond? Well, if your expected Q is less, okay, than plus Q, then actually what you need to do is that you need to now modify your chemical potential in such a way to balance, okay, so that your capital Q, so your expected value is actually equal, okay, to your conserved Q. So your system is always, changing your chemical potential to encourage either more particles or more charge to come into your system, or if you have too many charges in your system, then the chemical potential is changed so that it actually gets into the reservoir. Okay, so there is actually a good thermodynamical interpretation for this gradient ascent algorithm. So, and the number of iterations, okay, for example, you can see that, it would, scale with log of, the dimension and, the maximum value, of the charge. Okay, so, you can think about this as efficient, okay, in the size of the system. Okay, so everything that, we've seen, it didn't need to, it could have been done on a classical device. Okay, so if you're able to prepare, okay, if you wanted to solve your semi-definite optimization problem just on a classical device, then you can simulate a classical thermal state that we've seen before where the Qs don't commute, and of course we can do this gradient ascent on a classical device, and then so this is just like a new classical algorithm. But what happens when, the system is too large? Okay, so the corresponding n, is too large and the dimension, is exponential in this little n, then it would, then we think, okay, if it's not, it's probably not efficient on a classical device. Okay, in those cases, then we probably need to estimate things like, expected value of the Hamiltonian and the charge on a quantum device. And this would be the corresponding hybrid classical algorithm. And in these kinds of cases, we would, need several assumptions. Okay, so we need, of course, to be able to prepare the quantum state, the quantum thermal state, efficiently. And in particular, it needs to be at this temperature, okay, where temperature goes roughly as epsilon on n, where epsilon is the final error, okay, that you tolerate. And of course, we need efficient measurement of the observables, okay, of the Hamiltonian of the charge of the thermal state. Oops. Okay, so as an example, okay, so each of these observables, they're efficient simulable on a quantum device. For example, when the Hamiltonian is a sum, okay, of Pauli's, and so are the Q's, and we want, the sum to be, from 1 to, some polynomial, okay, in n, because if it's not polynomial, then it's no longer efficient. And you can show that the sampling complexity to estimate the observables to position epsilon, it's of course he has the expected, okay, log 1 on delta and 1 on epsilon squared, but the crucial thing is that it scales now linearly with the one norm, okay, of the h and the a's. Okay, so we want to make sure that those quantities are also poly n, okay, for this to be efficient. Yeah, so, and you can see, the gradient ascent algorithm for the hybrid, algorithm, it's, pretty much the same, okay, as for the classical algorithm, except that we need, extra steps. We need extra samples of the thermal state to actually measure their charge values, okay, so because, these expectation values come from sampling the thermal states. And because in that case, we don't have, exact values of the expectation values because they do come from sampling. Then here we use stochastic gradient descent or ascent instead of the regular gradient descent. Okay, and then we have a theorem, okay, for on the number of preparation of the thermal state, because now we need more just, coming from the sampling. And then, here you see you have, the regular sample complexity, but then you have to include, okay, the effect that you are, so you have, the log 1 on, delta and epsilon quantities, as well as the one norms of, the h and a's, as we saw before. Okay. And of course, there are also second order algorithms, possible and so on, but I think Dhrumil has a lot more to say about these, second order algorithms. And we can simply plug it back in into solving the original semi-definite optimization problem, okay, when we have, a bounded trace, okay, of x, because we just multiply things by r, okay, where r is, the bound, okay, on a trace of x. Okay, so following this, then with some of apart from Michaela and Mark, like all the other students are summer students in Cornell, working with Mark, and they actually, simulated, okay, some, examples for this. So one example is, the quantum Heisenberg model. So they did it for both 1D and 2D systems. So in this case, it describes interacting spin systems on a lattice. Okay, and you can have both nearest as well as, next to nearest neighbors, okay, of these. And then you can see for the Hamiltonian, for the total magnetization, each of the total magnetizations commute with a total Hamiltonian. Okay, so these are conserved sort of charges, but the total magnetization X, Y, and Z, they don't commute with each other. Okay, so these are non-commuting, okay, charges. So they fit within, our framework. And here, for example, for the 2D Heisenberg model with next nearest neighbors with 4 qubits, then, by applying the gradient ascent algorithm, then we see for both classical first and second order, as well as the corresponding hybrid, algorithms. So this is a plot of, how well they converge. Okay, and, it doesn't do too badly. And then, and this one is actually, when I was listening to Ángela's talk, it reminded very much of, something that, in this paper that we have that's called the stabilizer thermodynamic system. And it really comes from an observation, okay, of, when you think about quantum error correction, then we have things called stabilizers, okay, and stabilizers, that's an abelian subgroup, okay, of the Pauli group. So which means that the elements of the stabilizer that commute with each other, okay. However, okay, and you also have a set of logical operators that Right. So, and the set of logical operators are, subsets of the Pauli group where they can, so if you apply L with S, okay, that's equal to this, to S times L. Okay. And of course, this is what you need for logical operators because, you don't want your stabilizer to actually change, okay, your state after, it's been operated on by the logical operator. And this, we can think about as being mappable onto, a thermodynamical, non-commuting charge system, because we see that, H or S can commute with L, similarly to how H commutes with Q's, but the L's themselves don't need to commute with each other. Okay, so in the sense that, our Q's don't commute with each other. So this is the stabilized thermodynamical system where we have the total Hamiltonian, which is a combination of your stabilizers, okay, plus a linear combination of contribution from your charges, okay, which come from the logical operators. So then a simulation was done, for example, for 5-qubit error correcting code, and here when the gradient ascent algorithms performed, and then we see this is a plot for the convergence, okay, for those algorithms. Yeah, so basic summary. So why consider thermodynamics? Well, because it provides a physical basis for why quantum thermal states were non-commuting charges. Well, we can also think about them as a quantum Boltzmann machine, why they're important and natural for solving semi-definite optimization. Okay, so the idea is that semi-definite optimization is like energy minimization subject to constraints. And that we see is equivalent to free energy minimization when the temperature is low enough. And this free energy minimization is equivalent to solving a chemical potential maximization problem, which can be solved with gradient ascent. Okay. And there are many questions that come from this, or some of them include, how do we extend this to continuous variable systems, for example, and maybe broader classes or semi-definite programs, and maybe this might, also lead us to consider maybe a thermodynamically inspired implementation for these algorithms. Thank you. So thanks to Mark, Mikhail, and Dhrumil again, of course, and also to the summer students. And I'm in Shanghai, so you guys are welcome to come and visit us. We have open postdoc positions available. And actually, we developed a software recently called Unitary Lab, which we plan to put some of these algorithms on. We have those for PDs, ODs, and PDs as well. And we also have open positions there as well. Thank you.
Very nice talk. So any questions for Nana?
Hi, Nana. Actually,
Hi.
can you hear me? Actually have a thanks for the nice talk, and it's very interesting to see such an optimization problem. And I have a quick question about the last example in terms of the stabilizer Hamiltonians. Uh, is there any more words to say, more things to say about physical interpretation of this stabilizer thermodynamic system, or like it's an
Sorry,
interesting
what is your question?
Hamiltonian? So it's an interesting Hamiltonian that I didn't see that before, where each component is just stabilized operations, stabilized operators.
Oh,
So I was just wondering, is
um,
there any more physical interpretation of this Hamiltonian, or more physical
oh,
implementation of considering such stabilizer thermodynamic Hamiltonians?
So if I understand your question correctly, you're saying like firstly, is there somewhere else, right, where it's physically motivated that this Hamiltonian appears?
Yes,
And then
yes.
secondly, how do we actually implement this in real life?
Uh-huh.
Um,
Yes.
s-
So why is
that's
this physically interesting? Yeah.
Well, so originally, and maybe Mark can, talk more about this as well. So originally it was, thought of as a way of preparing ground states, okay, of these systems. So, instead of like directly cooling your system, then because when we think about um, uh, yeah, when we think about an optimization, if we think about, pre-energy minimization or energy minimization, we're really looking for ground states, right? Like subject to certain conditions. So then, but these constraint conditions, they actually correspond to, meaningful statements about, your stabilizer, your error correction system. So then you want to find ground states that satisfies these conditions. But then more discussions were made about, whether or not this is a sensible way, like, physically reasonable way of, actually making, such ground states. And I think maybe the answer is not so much. I don't know if Mark, you want to jump in on that one. But yeah, so that was the original, motivation for something more meaningful, like, for physical implementation. But yeah, I don't think it's clear on whether or not this is actually an advantageous way, but it certainly is an alternative way of doing it.
Okay,
Yeah.
thank you. Yes.
So I'll make a few comments. This is Mark. Regarding this construction of a Hamiltonian, this is Ángela presented it in her talk, and it's Kataev introduced this concept maybe in the late 90s. In fact, I think in the paper where he introduced the toric code. And so this concept of encoding a stabilizer in a Hamiltonian has been around for a long time. And I certainly saw it. There was a lot of interest in, I remember at QIPs, like in the early 2010s, there was a lot of interest in what's called a self-correcting memory, in which quantum information could be stored in a memory and preserved uh, almost indefinitely without uh, active operations. And so, like classically, the Ising model is a good example of this, where it's robust against perturbations of information encoded. And so it certainly came up in that context, and that was studied a lot. And I think eventually there was this Zhangwan Ha found this Ha code, and that was the context in which it was discovered. And so that concept had existed for a long time. One thing we were doing, and what Nana was talking about here, is through this concept of a stabilizer thermodynamic system, we at least talked about how the algorithm we proposed in our paper could be used for encoding quantum information in a quantum error correction code in like a physically inspired way. And so it's not clear to us, like Nana was saying, whether this would be useful in practice, but we thought it was an interesting concept. And so we talked about it in our paper.
Okay, thank you very much. Yeah, thanks.
Interesting. So any other questions for Nana? Okay. And yeah, due to the time, we just keep more discussions for the discuss session. Yeah, thank you, Nana. Okay, good. And we will move on. The last speaker of this session is Dhrumil Patel. Could you try share your screen?
Yeah, one second. Sure.
Okay. So Dhrumil is a PhD student at Cornell University. And I think he is very productive in like vibrational quantum algorithms, quantum machine learning, and quantum Boltzmann machine. And today we are very happy to have Dhrumil talk here. It's your stage. Yeah, Dhrumil, you can start.
Yeah. Thank you so much for the lovely introduction. First of all, good morning, everyone, and also good evening, depending on the time zone. Today I'm going to talk about natural gradient for quantum Boltzmann machines. The title also has parameter estimation, but I won't be able to talk about that due to time constraint. And first of all, thanks a lot for the organizers to the organizers for organizing this wonderful workshop on quantum Boltzmann machines. This work particularly was in collaboration with Mark, and this is the archive if anyone is interested to like take a deep dive into the technical details of it. So, okay. Like before, I would like to start, like before going to the natural gradient for quantum Boltzmann machines, I would like to first motivate the natural gradient as a whole. Like if you have a probabilistic model or if you don't have a probabilistic model, because here the quantum Boltzmann machine that we have is essentially a probabilistic model. Okay, and so let's begin with a motivating example. So let's say you have this loss function with two parameters, x and y, and it's given as 0.5 x squared plus 5y squared. For this particular loss function, you may notice that the coefficient with respect to x square in front of x square is very small compared to in front of y square. So if you plot this function on a 3D plot, it will look like this. It's sort of like a taco shaped where like the loss function with respect to y is changing a lot. Like if a small change in y essentially increases the loss quite a lot. But on the other hand, if you see like a with respect to x, like a small change in x, does not increase the loss function a lot. So if you try to minimize this loss function using the standard gradient descent, you will see this kind of a zigzag pattern here, and ultimately it will converge to the minimum point, the minimum. And you can also think in terms of like if you have a bowl which you start from here, it will roll on, it will go back and forth, and you have this zigzag line until the bowl will lose all the momentum and it will just converge to the minimum point. But the thing is that I really want to avoid this zigzag pattern because it will take a lot of iterations to do this. So is there a possible way to avoid the zigzag pattern altogether? So one thing is what you can do is that you can reparameterize x and y or rescale x and y in such a way that your effective function, loss function on that reparameterized version essentially looks like a bowl. Like here on the bowl, regardless of where you start, it will be sort of a zigzag pattern, but it's not like if you start with a very high y and it will be a lot of zigzag patterns. Here, it's mostly irrespective where you start, you will ultimately converge to the minimum point quite faster compared to if you start on the taco shaped rather than a bowl shaped. And this was also so natural gradient essentially was proposed by Amari in 1998, and he mentioned there's this one line in his paper where it's like if you use natural gradient learning, it might be easier to get out of plateaus than conventional gradient descent learning. Because like if you have a plateau with respect to a particular parameter, what you can do is like you can compress the plateau. Like you can think that there is a sort of a plateau here with respect to x, and we're trying to like compress all the points and making non-plateau look like. And this is not a plateau, this is like a steep direction. So you're trying to make it like a non-steep direction. So you can like rearrange your parameters and make it a good looking function. And people have also looked into like how this plateau, you can like escape out of plateaus for deep learning neural networks and all these things, like numerically. But still, we don't know. This is just like a might be easier. We don't know anything as to, like a strong proof of it. It might be interesting to see how it works. So this was just like a motivating example of why a different kind of a metric is useful, but we'll just try to formalize it more here. So natural gradient. So first, what I want to look at is like how do we essentially get the gradient descent update step that we all know, love, and we use it for all the optimization problems. So I will just look at a small derivation because it is useful to understand where essentially what things that we can change in order to like curve the space in a different way that we saw in our motivating example. So let's say a loss function is L of theta, where theta can be a single parameter or a multi-parameter vector. It depends on the problem at hand. And the gradient descent essentially what it does is like it looks at the linear approximation at some starting point. Let's say you are at a point theta m. And what it does is like it looks at the linear approximation. It doesn't look at the whole loss function, but it looks at the linear approximation. We are assuming that the function that the loss function that we have is smooth and continuous. So we can essentially do a Taylor expansion at theta m. So on the right hand side is a linear approximation of L of theta. Now, if you directly minimize this, it will lead to minus infinity because essentially this linear approximation is a line and it's unbounded. So if you directly minimize with respect to theta, the function on the right hand side of this equality, then it will give you minus infinity. So people what usually do is like they add a penalty term. And this penalty term is usually in terms of the Euclidean distance. Like what this says is that I don't want the new theta, which is theta m plus 1, the new theta, the new step, to be that much far away from my the current theta, which is theta m. But I also want the loss function to be minimized. So essentially, what we do is like we try to minimize this function with the penalty term. And if you try to minimize this, essentially like taking a gradient with respect to theta and setting that gradient to 0, you will get your famous standard gradient descent update rule, which looks like this, where eta is essentially like the penalizing parameter, but it turns out to be a learning step in the update rule. Now here, if you notice that in this particular step, in the third step, instead of using the Euclidean distance, like there is no special thing about Euclidean distance. You can use any other distance. If you use a Euclidean distance, then there will be some loss functions where if you have a small change in theta, it could lead to a very large change in L of theta. So this you can think in terms of our example before, our motivating example before, where a small change in y was leading to a large change in L of theta. But it can also be in the other direction, like a small change in L of theta might lead to a large change in theta. So what we can do is like instead of just thinking of as a Euclidean distance metric, you can substitute that metric here with a more general divergence between two different vectors, theta and theta m. But this changes the update rule. Now, if you do the same kind of derivation with respect to this, substituting here, it will be a different update rule. But I didn't write it here because I don't want to, I'm not interested in the general divergence between two different vectors, theta and theta m. I'm more interested in the general divergence between for probabilistic models because QBM is a probabilistic model. So let's say your probabilistic model is rho of theta. This is a general probabilistic model, and one example is a quantum Boltzmann machine. So I can change this linear approximation with the penalty into a penalty which penalizes essentially that this is now a distance between the probability distributions, or in general, this is a distance between two different quantum states, where rho of theta and the rho of theta m, which are parameterized at different points. Now, some possible divergences that we can look at is, and there are some popular ones, which is one is like a quantum relative entropy. This is the formula for the quantum relative entropy for reference. Another one is like a negative log Ullmann fidelity, negative log of Hollower fidelity. This is just like a rewriting of the Ullmann fidelity and Hollower fidelity. And finally, a more general version which encapsulates all the previous three is alpha Zerani relative entropy. So if you substitute any one of the divergences here and just redo the proof, I mean, there are caveats. It's not exactly the same kind of proof, but it almost works the same way. Then your update rule will be sort of like a natural gradient update rule. It's not just the gradient now, it's a natural gradient. And your update rule essentially will look like this. So if you substitute quantum relative entropy here and you redo the derivation, your update rule will have this a new thing, which is a blue, which is colored in blue, which is a Kubo-Mori information matrix, the inverse of that. The rest of the things are the same. So it's theta m plus 1, theta m eta, and you have the gradient, but you have to multiply this here. And similarly, if you do if you substitute other divergences here, you'll get different update rules for all these divergences. Now, the first one is just the Kubo-Mori information matrix. I think Nana also mentioned about this in a talk. The second one is a Fisher-Bure information matrix. The third one is known as, in the literature, Wigner-Yanesee information matrix. And finally is just a generalization of all the information matrices, which is alpha Z information matrix. Now, all of this are essentially quantum generalizations of the classical Fisher information matrix. The classical Fisher information matrix, essentially, we just have one quantity, but when you go to the quantum side, you have different kinds of information matrix, which in the limit lead to the same classical Fisher information matrix. Okay. So now the question is like, okay, like all these new things are introduced in the update rule, but how does this look like? How these are matrices. So how does these matrices look like? So let's assume that your probabilistic model, rho of theta, has a spectral decomposition, which looks like this, where your lambda k are the eigenvalues and pi of k are the projections on the subspaces of the eigenvectors. Now, because this is parameterized by theta, this too will also depend on theta, but for simplicity, I'm just avoiding writing it. But this too will also depend on theta. So now we want to know how this matrices look like. So matrices, the Kubo-Mori information matrix, it's a matrix. So the ijth element of that matrix has this particular form, where it depends on the eigenvalue, the eigenvectors, and also the partial derivatives with respect to the model that you're looking at. And similarly, the Fisher-Buret, Vigneriana, and alpha Z. I mean, I just like wrote this. These are scary looking expressions, but I just wrote it for reference if anyone is interested into like read more about it. Now, the question that I want to focus on this talk is, what if rho of theta is a QBM? How these matrices look like? That's the first question that I want to answer. And the second question is this, is that I want to estimate all the elements using simple quantum circuits when your rho of theta is a QBM. Okay, so that's the question that we'll focus on. Because all these are known in the literature, but we are interested in how this expressions look like when your rho of theta is a QBM, quantum Boltzmann machine. So briefly talk about the results that we have in the paper. So this is the paper, natural gradient and parameter estimation for quantum Boltzmann machines. And these are like the brief contributions. There are other things as well. So the first thing is to get the simple expressions for the Kubo-Mori and the Fisher-Buret for quantum Boltzmann machines. And the second thing is to estimate matrix elements of this matrices using simple quantum circuits. And the third that we looked into in this paper is the estimation of Hamiltonian parameters from thermal states. I won't be talking about this. I'll just talk about the first 2 points. Now, after that paper, there were 2 different extensions, 2 different papers on arXiv, which Michele, I, and Mark. This was the first one, which talked about the evolved quantum Boltzmann machines. And for this particular probabilistic model, which is a more general version of quantum Boltzmann machine, we get simple expressions for Kubo-Mori, Fisher information, Fisher-Buret, and Vigneriana, Fisher information matrices. And also we give like algorithms for estimating this matrix elements of this matrices. And finally, this was recently posted by Mark on arXiv, and he essentially extends or generalize the previous 2 papers, like to generalize to the alpha Z information matrices generated from the alpha Z Rayleigh entropies. Now, what essentially this results essentially will do for you is that this results will enable metric-aware quantum machine learning using QBMs or evolved QBMs. Metric-aware essentially is the natural gradient. Now you can use natural gradient because for natural gradient update rule, you require 2 things. One is the derivative of the loss function. Another one is the information matrices. Now we can estimate both of them. Okay, so that was the results. So before, now we'll talk in a little more detail about these things. But before going into the details, I just want to briefly talk about the notations that I'm going to use. I'm sure like everyone now knows what quantum Boltzmann machine is. So here G of theta is just a parameterized Hamiltonian, where the parameter vector is theta, and it's a linear combination of Gj, which are local Hamiltonians. And QBM, quantum Boltzmann machine, essentially is a thermal state corresponding to G of theta. And Z of theta essentially is the partition function. It's just to normalize this and make it as a quantum state. Okay. Like the first ingredient that we need, one of the ingredients that we need is the derivatives of QBMs. Why? Because if you recall, this was the original slide where I showed you the expressions, and this was the important ingredient that we need the partial derivatives. We need to figure it out. That's one of the ingredients. So we know that the partial derivatives of the quantum Boltzmann machines essentially has this particular expression, the thing that you see on the right-hand side, where this phi theta of x is a quantum channel. Why? Because P of t this is a probability density. And we call this probability density as a high peak tent probability density. The reason for this name is because of how the function looks like. It looks like a high peak tent probability density. So this is also known. We didn't come up with this. Like we came up with the name, but the rest of the things were new, were already known. But using this expressions for the derivatives for the quantum Boltzmann machines, what we can do now is we can get the expressions for Kobomori and the Fisher-Biore matrix elements. So if you recall, this was the original formula for Kobomori matrix elements. Now, when rho of theta is a QBM, we get this expression, where essentially from the scary looking expression, this expression essentially has like, it's a bunch of expectation values. So the second term is easy to estimate. If you have multiple samples of rho of theta, what you do is like you estimate Gj, which is a local Hamiltonian. And similarly, you can also estimate the expectation value of Gj, Gi and Gj with respect to rho of theta. Now, the first term is a little bit tricky, but in the paper, we give a way of estimating the first term as well. So for estimating the first term, what you do is like you sample T from the PT, the probability density that I showed you before, and then you just run this quantum circuit. In this quantum circuit, essentially you have the control Gj and you have this Hamiltonian evolution. But in this Hamiltonian evolution, this is a short-time evolutions. For most of the time, it will be short-time evolutions. Why? Because you're sampling your T from this density. And if you see outside -1 and 1, it's almost 0. It's exponentially decaying. So that the T that you will sample for most of the time, it will be really, really small. So it's efficient to estimate the first term. Similarly, we also give a way of the new formulas for Fisher-Biore and also a way of estimating Fisher-Biore information matrices. So recall this was the original expression that we had. And now when rho of theta is a QBM, we have this new expression. It almost looks like the previous expression of Kobomori. The second term is exactly the same, and you estimate the same way. But there is a difference in the first term. Instead of phi of theta of G of I, which only had G of I before. But that's the only difference here. And for estimating the first term here as well, what you do is like you sample T1 and T2 from PT, and then you run this circuit. So you do this multiple times, and that's how you can estimate. You get an unbiased estimator for the first term. And this is also efficient because if you remember, T2 minus T1 is not that large. So the Hamilton evolution is also for a short time evolution. Okay. So like that was all about how to estimate the matrix elements of the Fisher information matrices. Now let's apply to some task. Let's say I want to use natural gradient for generative modeling. So what is generative modeling? So for generative modeling, your loss function essentially has this form where you have a relative entropy between unknown target state and your ansatz, which is a quantum Boltzmann machine ansatz. For that, the natural gradient update rule essentially is just the same thing. Here, you estimate the elements using the circuit that I showed you before, and you estimate the elements, you construct the matrix, and you take the inverse of that matrix. And the second is you estimate the gradient of this particular loss function with respect to theta using the standard this is known in the literature, how to estimate this gradient. It's simple expectation values, difference between the expectation values. So using this, you can apply the natural gradient for generative modeling as well. Now, I'll just briefly talk about like the Hamiltonian learning from thermal states. I won't go into the details about the how to estimate the parameters of this. I won't discuss about the algorithms, but I just want to briefly touch upon it. So like given n copies of a thermal state, the Hamiltonian learning problem is that a rho of n copies of this thermal state, which is defined as e to the power minus ih theta divided by z, I want to estimate theta, or this can be a single parameter or a multiple parameter vector as well. So this is n copies of theta, and one can choose any measurement strategy. Your measurement can be like you apply measurement on individual copies of rho of theta, or your measurement can be you collectively apply measurement on all n copies. It's up to whatever strategy you want to use. And let's say after you use this, after you measure, your outcome is some m outcome, and using that you apply a function which is rho of hat of m, and this is your estimator of theta. Now we know that the quantum Kramer are bound, and like no matter what strategy you use, your covariance matrix, this essentially helps you in bounding the error between the estimator and theta. This covariance matrix is always lower bounded by the Fisher information, the inverse of the Fisher information, and the number of copies that you are using. So if given any Hamiltonian learning problem, if you want to get the fundamental lower bound of how well you can learn the states, it depends on the Fisher information. And we showed in this talk how to estimate the Fisher information matrix elements using this. And in the paper, we also talk about if this is a single parameter, we give an explicit algorithm for estimating that using the optimal measurement strategy in the paper. But I won't be talking about that here. Okay, I think that was mostly the things that I want to talk about. So for the conclusion and the open problems, QBMs constitute a promising ansatz for quantum machine learning. And in this paper, we derive like Fisher, Bure, Vignariana, Kubo-Mori, and other kinds of information matrices for QBMs. And we established like simple quantum circuits for estimating these quantities. And this essentially enables using QBMs in a broad variety of machine learning tasks. Now, for the open problems that I'm really interested in is to prove a concrete result on barren plateaus when using QBMs for a particular task, let's say ground state energy estimation task. So are there barren plateaus? Because we don't know of any result on barren plateaus on QBMs. Another thing that I'm really interested in is in the natural gradient approximations. Why? Because like in the natural gradient, what you require is you require gradient as well as you need to compute a matrix. So if the number of parameters in your model is quite large, let's say 1,000,000, then that matrix essentially is 1,000,000 by 1,000,000, and you have to take the inverse of that matrix. So are there any natural gradient approximations? Because these are known for the classical machine learning task. So it would be good to know if we can do this, like have some kind of result here as well for quantum Boltzmann machines. Thank you.
Thank you for a very nice talk. So any questions for Dhrumil?
Hi.
Hi. Oh,
After you.
thank you so much. I hope there's no noise from my side. I'm in a slightly noisy environment. Thank you so much, Dhrumil. Can you please comment on why you think evolved QBMs might be a better model than QBMs?
It's just a generalization of QBM. So in QBMs, essentially what you have is you have the parameters that you see. Let me just pull up. So the parameters that you are trying to learn or like that you can manipulate is this theta, which is like in the linear combination of Hamiltonian, right? But if you have a evolved QBM, you have an additional set of parameters. So your expressive power becomes more. Just if you just consider compared to if you just consider the QBMs. So that's why it's important to understand. So we also like it's a very interesting question because we haven't looked in. It's just a theory for now. Like we haven't looked into like how expressive it is, but it would be really good to know like if I compare the two cases where if I just increase the number of parameters here, and the second case is like if I keep the parameters here the same, let's say J parameters, and if I have an evolved quantum Boltzmann machine and additional parameters where your parameters is on the evolution operator and not the QBM operator, which one is more expressive? It's an open problem, but yeah, we don't know the answer to that.
Okay, thank you.
I'll follow
One
up on
last
that.
question.
Adit,
Sure.
thanks for your question. I'll just add another point. To add the extra Hamiltonian evolution is much cheaper than the thermal state preparation, right? And so part of the idea is that you can have some extra expressivity at smaller cost.
Yeah.
Oh, fantastic. Thank you so much. I have one last question about your
Okay.
natural gradient approximations open problem that you talked about. Do you have
Okay.
any specific analogs from classical machine learning that you had in mind?
So there are some algorithms. I didn't go through much about in the literature about these approximations, but I'm really interested in looking into it further. There was some like K-FAC kind of an algorithm, which is sort of like a low rank approximation to Fisher information matrices. So you don't need to compute the whole Fisher information. You just compute a low rank version of it, and then you invert it. So that's one. Another one is like if you know that the parameters, a set of parameters, let's say the theta vector is a set of parameters, and if you know that some of the parameters are not very highly coupled with other parameters, then you can compute, you can essentially block diagonalize the Fisher information matrix, and then it's easier to invert it. And there are other approximations, like for example, the Adam optimizer that we see is also, you can think in terms of a natural gradient. It's a first order approximation to the second order natural gradient algorithm. Yeah, so the different kinds, but I haven't looked much into details about it. But yeah, it's a
Okay, thank you. I will send you an email. We will talk later.
okay, sure.
Sure.
Hi, Dhrumil. I have a question. It seems that the estimation of the information matrix is quite time-consuming, since each element is independently estimated. Such, requires additional thermostat sampling. So, are there any decisive, provable, or practical improvement from the perspectives of runtime or the thermostat sampling?
Yeah, for now, this is the results that I proposed are for like general Hamiltonians and general QBMs. Like if you know certain structure of the Hamiltonian, it might be the case that, as I mentioned before, like different kinds of approximation for natural gradient, right? Like if your certain parameters are not coupled with other parameters, then essentially you can decouple them and you can have a more efficient Fisher information um, matrix, which you can invert it. Yeah, but you need to know certain structure about it. The results that I presented here, they are for general QBM ansatz. But if you know certain structure, yeah, definitely you can do it. But I can't say for certain because I haven't investigated into this much. So yeah, it's an open problem. But it's a good question. Thank you for that.
I see. Thank you.
Yeah.
I'll follow on that. There was a paper of oh boy, his name is Sandeep Pradhan and his group. He's a professor at University of Michigan. They had a paper, I think it was called Coordinate Natural Gradient Descent or something like that. There was a way they were trying to use fewer samples and try to realize effectively the same directions of natural gradient. And it seemed like an interesting idea. I think it had its roots in classical machine learning. And so it would be interesting to investigate that direction further. There's also I can't remember his name, but there's someone who's been posting a number of quantum natural gradient descent papers within the past year, not related to QBMs, but more so, I think, for parameterized circuits. And I think he was trying to reduce the overhead of natural gradient as well. I can try to dig those up and post them in the chat.
Yeah. Thank you, Mark.
Thank you very much.
Hey,
Great.
Dhrumil, I wanted to ask a question, or maybe not ask, but like kind of brainstorm on like a little bit on this. So I was thinking, so you motivated initially the natural gradient descent on this convex example, but I would imagine actually like natural gradient descent to be more helpful if you have a non-convex landscape. So like it would help you like avoid some of the local minima and so on.
Yeah.
So like it will go again in the same direction of like when you have a convex loss landscape, to me, it doesn't feel like it's worth the trouble, because yeah, you may have those like zigzags that you showed in the beginning, but like we know that eventually like we are going to reach. So like it maybe is also not easy to prove in terms of the like number of steps that you would need in terms of convergence. So especially you showed this example on generative learning where you have like the fully visible scenario of like the gradients, and like the like paper from Koopmans and Benedetti, they show that the loss landscapes is indeed convex in that case.
Yes.
So like can you comment maybe a bit on that?
Yes. Thank you for the question. Yeah, but actually, like people have looked into, so let's just forget about the non-convex for now. If you just look at the strongly convex version functions, right, they're easier to optimize. I completely agree with you. But the thing is that if you look at the iteration complexity, the number of iterations that you need for the GD, the gradient descent to work, it depends on a particular parameter which is called kappa. It's a condition number of the function, and that kappa essentially what it does essentially is a ratio of the how steep a curve is with respect to one parameter compared to how flat the curve is compared to other parameter. So if you have more steep and more flat, then your kappa there are cases where it's even exponential, right?
Okay.
So natural gradient essentially if you and people have also looked into the strongly convex functions for natural gradient, and it is independent of kappa.
Okay.
So it doesn't hold for that. But obviously, you need to pay for it. What paying we are doing is we are computing this Fisher information matrices. So each iteration will be slightly expensive, but you will converge faster.
Yeah, but I guess like it's difficult to say if it will like the total cost will be cheaper or not without trying. I guess like it depends on the problem
Yeah.
as well. So
Yeah. That's true. Yeah.
yeah. Okay. Thank you.
That's good. So any more questions for Joe? Okay. Oh, good. So next we will move on to the discuss session. Okay. So we'll just go to the one by one the speakers who talk today. Okay. So anyone? So the first speaker today is Mingrui. Could you like prepare for discussions?
Yeah, so I'm open for the problems.
Okay. So any more questions for Mingrui?
I have two questions, please.
Yeah, go
Yes,
ahead.
please.
Um, One question is from the absence of my knowledge in this field, what you mean by saying quantum data physically? And the second question is, I heard about control. Which kind of control techniques do you use? Do you use quantum control or classical control?
Okay, so for your first question, quantum data. So in our model, the quantum data just represent as, the Hamiltonians, or for example, the Hamiltonian for some many-body systems, because we know that the data of all the information of the system was just encoded in some Hamiltonians, right? So for example, in the SPD phase detection, you can treat the lambda or the parameters in the Hamiltonian as the data. And then the whole Hamiltonian evolution would be the quantum data, which we represent in the model. And secondly, for your second question, would you talk about can you repeat it?
Um, uh, 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 do you use control? And if you use, which kind of control techniques do you use? They are classical or quantum?
Oh, okay. So in our model, the control is really the control evolution, which is quantum, as you think. And the technique we're using is I think we just use this
Optimal
technique called,
control.
yeah, the optimal control thing.
Okay, thank you very much.
No worries.
Good. Any more questions for Mingrui? Okay. If not, we move on to the second speaker, Angela.
Hi, Anoa. I
Hi,
have
Angela.
follow-up questions.
Hi.
Would you mind
Yes.
to share your slides?
Yes. Can you see them?
Yeah.
Okay.
Actually, my first question, I don't know if it necessarily needs the slides, but last night in the US and I guess this morning in China, we had a talk from Jiaqing Jiang, about her work on thermal state preparation, in particular the metropolis approach. And I was actually in Cambridge in May. There was a information theory symposium or something like that, and I was talking with Frank Verstrade about these things, and he expressed his opinion that the methods, all the methods are interesting, but his opinion was that the Lindbladian evolution approach that is attempting to mimic nature. And what was remarkable about the metropolis algorithm approach is that it's doing something smarter than nature and can converge faster. And so I'm curious to hear your opinion on this. And if you have any comments, I don't think you compared the approach to what Jiaqing, the metropolis approach. And so, yeah.
Yeah, so it's a very, very good point. No, I mean, well, the two papers that I mentioned here, actually the second one is with Frank. So you see that he's in the dualities part, not in the dissipation part, precisely because of what you're saying, no? Because he's not very, he's a bit pessimistic with respect to the dissipation approach. Um, the when we have discussions, my position is a bit different in the sense that I'm happy with things that you can prove. Um, in the case of the metropolis algorithm, there's evidence that it converges faster than dissipation for multiple examples already in the classical case, but there's not an analytical proof of that. So that's something that is fully missing, even in the classical case. And of course, we like dissipation because mathematically it's hard to prove, but it's very clean in the sense that you prove something and then you know that it's going to work, no? Because it's already proven. So this is why we typically use dissipation instead of something like metropolis, for example, because even classically, there's some intuition for some systems that it works pretty well, but there's no proof. There's no guarantee of the optimal bound that you can get using something like the Monte Carlo Markov chain. No? So that's why, well, even in the quantum case, there's again in this work of Jacking, there are some things that you can say no, and it's very nice. I mean, I really like this approach as well. But you cannot prove bounds like the things that you can do with dissipation for specific models. I mean, beyond things that are like very very easy models.
Yeah, there was also the algorithm that she outlined yesterday was remarkably simple, such that
Yep.
you could actually imagine teaching that in like an introduction to quantum computing course. And so I'm tempted to do that next semester. So that was a nice aspect. Another point that came up during the discussion with her is throughout the workshop, there's been a lot of interest in using quantum Boltzmann machines for generative modeling. This is where you're trying to use it to simulate a probability distribution or to simulate a quantum state. And there was, it came up in Cenk's talk, who was just speaking, that classically it's observed that you really need to use Boltzmann machines with visible and hidden units. So visible ones are the ones that you measure or that are trying to like simulate the state. And these hidden ones are like an inaccessible, or they're like a reference system that eventually you just trace over, right?
Yeah.
And so um, to optimize the parameters of the Boltzmann machine for the generative modeling problem with hidden units, classically, if you read work of Hinton and what Cenk and his co-author Maria were talking about is the predominant method now for optimizing restricted Boltzmann machines is this contrastive divergence method, where the way you don't sample from the Gibbs distribution on the visible and hidden units. They say that's like too expensive. And what you do instead is this back and forth where you take the data for the visible for that you have and initialize the visible units to that data, and then you use the conditional probability distribution, the conditional Gibbs distribution for the hidden given the visible, and you randomly sample the values of the hidden units in that way. Then you go back, given the values of the hidden units, you sample the visible units according to the conditional Gibbs distribution. And what's nice about this is that these conditional distributions factorize nicely, and so they're efficient to sample from. And so this is putting you on the spot, but I don't know if you have any thoughts about how to do this kind of procedure in a Lindbladian way, where you would kind of go back and forth like this. Do you follow what I'm saying?
I followed it for sure. I've never thought about this before.
Okay.
uh, I think it's a very interesting thing, no? So because it's not so far, at least what I understood from what you said, is not so far from this idea that I was saying before, no? That in the toric code case, for example, you have something that tensorizes, and then in a sense, studying dissipation towards the whole thing is the same as studying dissipation towards the parts, and then putting it together in some sense, no? So that doesn't sound like extremely different to me.
Mm-hmm.
I well, I haven't thought about these things before. I don't know anybody that has done it, but I could imagine that maybe this is the direction to go. Like construct dissipative processes converging to each of these parts that you're saying there,
Mm-hmm.
and so that they are. I wouldn't even know exactly how they would be like from the top of my head, no, but so that they merge properly, so to say. So I don't know. Maybe this is something that one could think about. Yes.
Yeah. In the talk of Maria yesterday, they considered the case of commuting visible units, the
Yeah.
terms in the Hamiltonian, and things somehow simplified for that case. And they spoke about a way to do this back and forth. And I think you had imaginary time evolution there, right, Cenk?
Yeah, that's correct. Yeah.
And so there's a question whether that part could somehow be replaced by this Lindbladian
Yes.
evolution, right? In some way, you know.
Going back and forth with Limbladians always sounds pretty problematic because, well, you don't
Mm.
have adiabatic theorems for Limbladians in general, right? Because inverting Limbladians is something that you cannot do in general. But of course, for some easy models, sometimes you can construct something that is very similar.
So that
Some,
property you basically obtain because of the connectivity structure. So in that case, so we have this like standard RBM like connectivity. I'm not sure if you're familiar, Angela, with that.
yeah,
So you basically can like if you set the visibles, the hiddens basically become a disjoint graph. So you have like and like with that it becomes like something that you can factorize. So if you had connections between like the hidden units or the visible units, then you cannot really do it. So even if you consider a 1D like commuting Ising model,
yeah,
then you technically cannot factorize because like there will be that connection.
okay,
But I think people are looking into it. Like I also know like so these algorithms like contrastive divergence and also belief propagation. I believe people are using for commuting Hamiltonians in general.
yes.
But the cases that you consider are, I think, more complicated because of the connectivity patterns.
Well, but that's good, I guess, no? Because if you take if you have commuting algorithm, commuting Hamiltonians, as you're saying,
Mhm.
and they even have like some simpler geometry, then for sure something similar to what we are doing should be
Oh, I wouldn't call
feasible.
it's like simpler. It's different because it doesn't really fit into the like definition of like 1D, 2D grid like things, right?
Okay, fair
Because
enough, yeah. Yeah, but still, many of the things that I was showing here, I was presenting them in square lattices because it's easier, no, to visualize. But of course, many of these things extend to graphs that are reasonable, with not a very high growth number or anything like that. So maybe,
yeah, I just randomly Googled like I seen some like now block belief propagation algorithm for two-dimensional tensor network. So I think like similar ideas people are like using
yeah,
like some papers come up when you search for it. So it may be interesting.
yes, no, definitely, yeah.
So
Yeah, I
Anna,
mean,
oh, sorry, go ahead.
sorry. I was just going to say that this limitation that I was saying about going back and forth, I mean, for some of these slightly simpler models like commuting Hamiltonians and with graphs that are more or less controllable, if you consider certain Lindbladians that have nice properties, sometimes you can create like some sort of pseudo inverse that essentially inverts everything except for the fixed point. So maybe you don't have a full adiabatic theorem, but you have something that is pretty similar in the domain that is good enough for you. No? So maybe this part is not extremely problematic either.
Okay. I had another question, which actually was useful for your slides. Back to the modified logarithmic sublev. I guess you've studied work on contraction coefficients.
Yes.
So this strikes me as a like continuous version of a contraction coefficient, right?
Yeah, in a sense, yes.
Okay. Did you come across, we had a paper called, and with Christoph, who I
Yeah.
think is on the line, on quantum Dublin coefficients.
Yes, I saw that at some point, yes.
So we were trying to think about how to generalize our findings to this continuous setting, and we had some thoughts there. But I'm curious, have you ever thought about that?
No, not directly. No, I've most looked at your paper to use it like for some other applications, like when doing things related to strength and DPIs and all these things, but I've never tried to do it for this framework.
Mm-hmm. The alpha L, is it,
Yes.
so that's a function of L. And coincidentally, we use alpha for the Dublin coefficient also, I think.
Oh.
Is that, what kind of function of L is that?
So that's linear with L. Because this
Uh,
is essentially, I mean, this is defined from differentiating this with respect to time. So this is
mhm.
essentially given by minus the trace of L of sigma and then log of rho, sorry, log of sigma minus log of rho, and everything divided by the relative entropy, by twice the relative entropy between
Oh,
sigma and
okay.
rho. So this is just a trace of L multiplying stuff, so it's linear with respect to L.
Is it possible for you to bring up something that would show us that expression?
Yes, one sec. Yes.
I also see Thashani on the line, who was also our co-author on quantum Dublin work.
Yes, so the expression is this one here.
Oh, I see.
Now here I exchange the roles of rho and sigma.
Interesting. I will take a screenshot of this. So the advantage of Dublin is that it gives an STP, right? And it's not clear to me looking at this whether this would be efficiently computable. Do you have any comments along those lines?
I know that there are some people working on that precisely, on
Okay.
seeing whether you can create some kind of SDP or just use convex optimization to try to compute these quantities.
Mhm.
And I know that they've been doing this for a while, and I don't think for them it was extremely easy.
Okay.
Because, they've been doing that for a while and there's no paper out yet. So,
Mhm.
so I don't think it's very easy.
I see. But the slide you're showing, this is I guess it's a relatively simple derivation. It's just a
Yes,
derivative calculation. Okay.
it's really that. So it's you start with the relative entropy between the evolved state and the equilibrium, and then you differentiate with respect to time. So then when you differentiate with respect to time, you get this expression.
Mhm.
And then what you know when you look at the relative entropy, now plotted with respect to time, is that in the limit, I mean, this is always going to be larger than or equal to 0 because these are two density matrices.
Yeah.
And in the limit, this is actually going to be sigma, so this is going to be 0. And because of data processing inequality, you know that this function with time is monotonic, monotonically decreasing, strictly non-increasing, no? So it's something like this. So that means that the absolute value of the quantity itself is going to decrease, and the absolute value of minus the derivative is also going to decrease with time. So you can essentially construct an inequality between the quantity itself and minus its derivative, and try to find an optimal constant that makes this inequality true always, like for every state row and for every instant of time. And if this thing exists without being 0, then you call this the optimal alpha, you call it a modified logarithmic Sobolev constant. And the expression is this one. So this, as you are saying, it's really easy to compute.
Yeah. One thing, I'm getting a little sidetracked maybe, but one thing we did in our quantum Dublin paper, it was related to something we saw in a paper of Combi's, is we allowed for a reference system, and we defined, or we generalized this complete contraction coefficient. And I think there's a complete modified logarithmic sublev, right?
Yes.
Is that useful at all in the context of thermal state preparation?
It's pretty useful. The complete log Sobolev inequality is, I guess, it depends on which procedure you follow to actually prove the existence of modified logarithmic Sobolev inequalities. But for us, what we always do in our strategy is some divide and conquer strategy that is called, no? Which is that you start with a lattice, and then you take a sublattice of it, and you reduce your system to it, so to say. So I don't know, I think I have it here later, so maybe I can actually show you some picture. Yeah, so something like this, no? So you start with lattice lambda, and then you have a subregion A, and what you want to do is relate the modified logarithmic Sobolev inequality constant of lambda to that in A, because this is something that classically is done. And classically, what you can see is that you can lower bound the MLSI in lambda with the MLSI in A by paying some price of a function that depends on the cardinality of A. But quantumly, this is not what happens. What happens is that now you can lower bound the MLSI in lambda by something that here I call conditional MLSI of in A, so of lambda in A. And this is essentially given by this definition here. So the terms of the Lindbladian that you are considering now are those that are supported in A and the boundary of A. And now here you have something that is a conditional relative entropy instead of a relative entropy. This is why we have this conditional MLSI, no? But the point is that, of course, one thing that you can do now is just take the difference between A and lambda to be arbitrarily large. And if you take that to be arbitrarily large, and now your L is L in a tensor identity everywhere else, and this is arbitrarily large, what you have is actually the conditional version, the complete version of it, no? So let's say if you have a complete MLSI, this implies this conditional MLSI. And what we actually see is that the conditional MLSI implies the MLSI that you're looking for. So this is why having a complete MLSI, I mean, as a summary, having a complete MLSI implies an MLSI. It's something that is stronger. Up to this reduction procedure, which is highly non-trivial. So this inequality that I'm writing here, it has a lot of things hidden, but this is a procedure that we usually follow.
Thanks.
Sorry, I have questions, many questions. One is so it is a very interesting and beautiful talk, and
Thanks.
and I understand that your work touches the problem of toric code models to use for quantum computing. But what about another aspect to simulate toric codes in quantum computing devices? Are these practically important?
Well, my work only touches exactly what you are saying, no? So the preparation of Gibbs states and ground states of the toric code. So just that, no? So cannot, for example, so our work doesn't directly simulate the Hamiltonian of the toric code or anything like that, no? So it doesn't go in that direction. But one thing that I didn't mention here, which is typically the main motivation to study dissipation towards the Gibbs state of the toric code, is actually going in the opposite direction. Rather than simulating the toric code itself, it's more because you want to study what happens if you try to use the toric code as a candidate for a quantum memory, no? And so the idea there is that if I now encode some information of a system in, let's say, the ground state of the toric code, for example, and now I let the system evolve with this quantum Markov semigroup that I was mentioning before, then what you know is that this is going to converge very quickly to the Gibbs state, because this is what we are proving there. And what this is essentially telling you is that the information that you stored in the ground state is going to be lost very quickly. So essentially, it's a way to say that the toric code in 2D shouldn't be used as a quantum memory because it doesn't have time to do error correction. So actually, this is something that in this other talk we mentioned, well, I mentioned at some point, I mean, is that if you have rapid mixing, you have no error correction, so to say, no? Because to be able to perform self-error correction, you need a mixing time that is exponential on the system size, and having these results of logs of inequalities gives you a mixing time that is logarithmic on the system size. So it's something that is totally different, you know? So this is good for efficient implementation, but this is pretty bad for quantum memories and self-correction. So it's not directly implementation, as you are saying, but this is the motivation why we look at that.
Do you compare with existing quantum memories in quantum communication, if you heard about that, from the well-known paper in Modern Physics Review?
So no, we don't directly compare to that, no. So this is more of a criterion of no-go results, in the sense that if you have a certain model and then you show that you have rapid mixing, which is what we do with these tools, then you know that this model is bad for error correction. But we don't have any result on the opposite direction, something that says, oh, now we mix very slowly, so that means that this is good for error correction. We don't have anything in that direction.
Okay, and my second question. I'm wondering, your talk gave me some ideas. I'm wondering if it is possible to create analog to quantum Boltzmann machines for non-thermal states, and this opens new opportunities and directions in the fields of, I don't know, quantum light, quantum squeezing state, quantum vacuum state, or quantum imaging, or also for magnons, if you know, spin waves, which have both bosonic or fermionic properties.
I mean,
Did
it's definitely an interesting question, but I've never thought about this before.
actually you mean to go from probability to density matrix and
No, well, the relations that you're saying there, no? The relations of this work with to all of this, I've never thought about that, so I have no idea.
yes, this just come to my mind. So, and some stupid question. I don't understand the negative. I heard about that, but I don't understand what is negative temperature physically mean. Can you explain?
Negative temperature, you see that I always work with positive temperature, so I think I'm not the right person
How
to
it
ask that.
can
Sorry.
be negative?
Yeah, sorry. I think I'm not the right person to ask that because for me
Okay,
the temperature is always positive or zero. They are
okay.
never negative. So
Angela, I have a question that I just thought of that I'm hoping you could answer. It seems like it would be so you've seen all these talks on, or some of the talks on quantum Boltzmann machines where we have parameterized thermal states. And then for some of the algorithms, we need to tune the parameters. And so it seems like it would be useful suppose you've prepared a parameterized thermal state, and you just want to tune the parameters a little bit. Do you have a sense of how algorithms could be instantiated to do that without having to do the full rapid mixing to start to make it from scratch?
Interesting, yeah. So just tuning these parameters a little bit, you mean?
Yeah. Like I think, I've looked at some of your papers, you talk about like these perturbations, and so it's that kind of thing.
Yeah, that's what I was thinking, no? That in that
Mhm.
case, I guess perturbation theory would probably be the easiest. So if you're perturbing just some specific things in the model that you have, I guess I would just look at perturbation theory of whichever figure of merit you're trying to compute there and see whether this is stable, no, against the perturbation, which is, I don't know, it's typically the case. For example, if you're perturbing something that goes inside a Hamiltonian, then this is typically going to be the case. That now, if you measure local observables, then this is going to be stable.
Yeah, but the question is, do you have a sense of how to modify the algorithm to realize that perturbation?
Huh, I see. Yeah, that's a good question. I guess that would depend on how much the perturbation affects, but yeah, it's complicated because if it's a perturbation that ends up falling in some very small part of the circuit, for example, then I guess you can just insert whichever gate is modifying that part. No? But if
Hmm.
it's a perturbation that is everywhere, which is what I'm assuming that is happening here,
Hmm.
I'm not entirely sure how to do this, like with the algorithm itself.
Okay,
No, I don't know, sorry.
thanks.
Yeah, thanks, yeah.
So just following on from that, Mark. So and I guess it's yeah, like yeah. So this is not terribly well thought out, but I'm just thinking of a really simple example where one of the tunable parameters could be say temperature, or it's like some constant right before the global Hamiltonian. And we know that physically we can think about ways of like if you prepared a thermostat at one particular temperature, how do you make it into one of another temperature, right? Instead
Yeah.
of like resetting, or you put it into another bath, right? And then let it thermalize. So for particular, types of parameters, I think there can be like physically motivated ways from which then we can make them into algorithms, I guess, because there are cases where we know that it has to exist, right? Because we
Yeah.
know physically that that's what happens. And it brings me to the other question about so when you have non-commuting, like so if you have your Hamiltonian that's, a sum of non-commuting components, so I'm wondering about that because I know that in the quantum thermodynamics world, it's actually not clear if, in some cases there would even exist any like Lindbladian type interaction, right? Where they would like, because this is the big question in quantum thermodynamics, whether or not, this thermal state with the non-commuting charges, it can really be called a thermal state.
Yeah.
Yeah. So I'm wondering what you think about that and whether or not you have like can think about no-go theorems, because if there are no-go theorems, then it would actually imply that maybe there are cases where they can't actually be called thermal states for a certain, collection of non-commutative charges.
Yeah, it's a very good question. I mean, if you're taking like non-commuting Hamiltonians that are, you know, um, on square lattices, not even square lattices, but some graphs that are normal, like as I was saying before, like properly behaved or something like that, and they are done over spins, so not fermions, not bosons, anything like that, like really over spins. Then you can always engineer this Lindbladian that I was mentioning at some point, this CKG Lindbladian, and this is something that is always going to be quasi-local. So if you have something that is finite range, you can always engineer this Lindbladian, and
Okay.
it's going to be such that this state is going to be for this Hamiltonian, you're going to have this state is going to be a Gibbs state, and this is going to be the thermal state associated to this Lindbladian. No? So I don't know if the example that you have in mind is something that is a bit more pathological than that.
Yeah, because I know that like in that literature, like that they would have these examples where you can show, okay, for these type of interactions, like you would, equilibrate to this thermal state. But but for more like general classes, I don't think it's known from my understanding in that community. It's not actually proven,
Yeah.
right? For all cases that you actually, it can actually be called a thermal state. Like you can, like there exist Lindbladians in which, yeah, it thermalizes. Yeah.
Yeah, so I guess then the pathological cases would be something a bit more complicated. Like as I was saying, like with some with some more complicated geometry or defined over bosons or fermions or something like that. Or even if you look at interactions like if non-commuting interactions over spins, there may be something that has a very long range,
Yes.
like long range correlations between spatially separated spins or something like that. And then in that case, yeah, I could believe that there's some no-go result for that. But for all the models that are a bit more normal in the sense that even up to long range, but with power law decay that is of order that is really larger than the dimension, you can still generate these Lindbladians. I mean, it's in a series of recent works, no? But you can always generate these Lindbladians that have them as a fixed point and actually as a unique fixed point, no? So they thermalize to them.
Okay. Oh, cool.
Yeah.
And I guess for these pathological ones also, like if you, yeah, like to create those states, like would you think about some kind of two-step procedure where you would, find the closest, thermal state approximation and then apply some other unitary.
Exactly. Exactly. So in these cases, at least what I typically do is find the closest easy model, so to say. So the closest Hamiltonian that is actually tractable by these techniques, and then do perturbation theories to see how much the error that is made from approximating one Hamiltonian by the other affects everything that you are doing after that. And in particular, if you can show that the mixing time is stable against this perturbation, then you can actually work with the easier system and still extend the result to the more complicated system. But this is, I mean, it's not only me working in that, there are like a lot of people working in that, and this is a quite complicated problem. Stability of mixing times with respect to perturbations. No? So that part is a bit more complicated. Stability only on the Hamiltonian side is much more explored, and there are many more results. But on the Lindbladian is much more complicated. So I wouldn't say that there's a lot of information there that can be used.
Okay. Cool. Thank you. That was
Thanks.
very cool.
Yeah, very nice discussions. Okay,
Thanks.
so thanks, Angela. Yeah, so we'll move on. And then is Nana. Any more questions for Nana?
Sorry, Nana. Am I right that it was something in your talk related to Lagrange multipliers? Am I right?
Oh yeah. Yeah, we used Lagrange
Yes.
multipliers.
So
can-
as I know, it is used in support vector machines, but anyway, you need to have some constraint when you do use these Lagrange multipliers. And um, what is the constraint in your optimization that you use?
Oh, well, so Lagrange multipliers are actually used as a tool. Like if you have, a minimization problem, and then you want to include a constraint, a Lagrange multiplier is a way of naturally making it just a single um, optimization problem without constraints, so that you're building the constraint like within the optimization problem. So I can share my screen. Yeah. So if you see, like this is a slide you're talking about, right?
Yes.
Yeah, so if you look in the first problem, like if you have a minimization problem, but then the little two dots beside it, that's a constraint condition. But if you, so which means that you can't just minimize, the quantity like on the left, because you have to take into account your constraint condition. So a way of kind of avoiding trying to, satisfy two things, right, at the same time is to make it just into a single minimization problem. And then this mu here, so these are called the Lagrange multipliers. And the idea is that now when you're minimizing this whole function, you also now, in addition, if you were also to minimize, or if you were to also maximize this mu quantity at the same time, then the solution of rho that you have, right, which is a function of mu, that would be the optimal solution to the original problem. So that's where it comes in.
Okay, thank you very much. And also about imaginary time evolution, as I understand, in that case, Schrödinger equation solution gives not unitary evolutions, but special Lorentz or Lorentzian evolutions. How this difference is used in these problems?
So here I don't actually, we don't actually mention anything to do with imaginary time evolution. I mean, the only relevant part is in the creation of these thermal states. So Ángela talked about a method where, you use, dissipative dynamics. So meaning, when you normally think about how thermal states are created, you think about a system and a bath, okay, and the system and bath interact, and then you create it that way. But an alternative way of making these thermal states, which is what many people looked at before, is to think about non-unitary evolution. So this is the imaginary time evolution. And in fact, I have papers on this too, where you create these thermal states by unitary evolution first, and then you trace out. Right, so that's where imaginary time evolution comes in. But with respect to this talk, like we just assume that somebody like creates these, thermal states for us, right? Yeah. So we don't, it's our algorithm is kind of agnostic to how these states are created.
Thank you.
Hi, Nana. May I ask
Oh,
a
hi.
quick question?
Oh yeah, absolutely. Yeah, sorry, I didn't realize this discussion was a question answer thing. I thought it was free discussion, but yes, sorry, go on.
Yeah.
Yeah, because we have others.
Can you
Yeah.
move to the slides of the optimization problem?
Um,
Mm.
I think we just lost Nana. I actually didn't hear your question. Maybe I could try to help.
Okay, so I was wondering, like, can we replace? Oh, she's back.
Nana's
sorry,
back.
I don't know what happened. I don't know why I dropped out. Sorry, let me. Yeah. So we have so we have a couple of different optimization
Actually, I
problems.
was
We have
asking to repeat the question because I didn't quite catch it. I was curious to hear it.
Oh, I don't think. I mean, you haven't asked your question yet, right?
Yeah, I haven't asked a question. So could
Oh
you move to the
yes.
slides for like the free energy optimization problem?
Oh, free energy. Okay, you want the free energy one? Okay, because we have a couple of different
Yeah,
ones. So
page
it's probably
15
this.
maybe. Yeah. So here, just wondering, like, for this, so this Qi are the operators for the constraints, and I was wondering, like, if we can, so in general, can we like apply this minimization to, with some, general resource theories? For example, the Qis are some constraints related to the resource.
Oh yeah, I mean these QIs can be whatever you want. I mean they have to be, Hermitian, they're observables of the system. But this is very general. They can be whatever you want. It's just I guess you should think about, so instead of looking at this problem, I mean I think just looking at the original semi-definite optimization. So our method is really for any semi-definite optimization problem. So again, your constraints, right, of this form, right, can be whatever you want. Like, I mean, it's not whatever you want, but it's as general as semi-definite optimization problem. So if you can rephrase your problem in that way, it can be applied. Now, the only caveat here is that, like, at least for the quantum part of the algorithm, like to transform this so that we're preparing a quantum like rho, then of course we know that rho has, trace one. So which means that trace of x, right, it has to be it's like a finite trace. So yeah, so if you want to extend this to continuous variable systems, that's something to think about, like how to do that. Yeah, but other than that, I would say it's as general as your, semi-definite optimization problem, like your typical one. Does that make sense?
Yeah, that makes sense.
So
Um,
I'll interject if just with a little remark. Regarding the QIs and the H's being anything, in order to have a possibility for an efficient quantum algorithm,
Oh,
they
sure.
should
Yeah.
have some structure. Otherwise, the thermal
Oh,
state
yeah.
preparation
Oh,
algorithms,
I did. Yeah. So let me
you
go to the
probably
relevant
mentioned that.
slide.
Yeah.
Yeah. So okay. So these are the assumptions. Okay. So for your so we had the classical algorithm and then we have the hybrid, classical quantum algorithm. But for the quantum one, so an example would be, so if each of the observable like H and Q, so if your H, for example, is a linear, it's a sum of your Pauli operators. Now, what you need to do is you need to estimate these observables efficiently. But we know that the sampling complexity of that's gonna go as the one norm of the coefficients right in front of the A's. And we also want, so therefore the sum, okay, of the Paulis, that has to be poly n, where n is the number of qubits in your system. And also, of course, that also the actual
mhm.
sizes of the individual coefficients A of I. All right.
Okay,
So this is if you want efficiency. If you also want to consider efficiency.
thanks.
Yeah. So good remark, Mark.
Thanks.
Um,
Ooh, any more questions? So have you tried this kind of SDP algorithm on some real devices?
No, because
Or how
so because
far
we have
is
trouble.
kind of end-to-end
Um,
design?
we have to, I mean, I think the main issue is actually making, okay, so there are two, there's the issue of, the main issue is really
Uh-huh.
making these
Gibbs
states.
state.
I mean, of
I
course,
see.
in principle, we can have, so Mark, you can interject again. So in principle, when we have like small qubit systems, like you
Yes.
saw some of the simulation results, like the Heisenberg model, for example. So I'll give an example. So sorry. What happened to the Heisenberg model? Yeah. So actually the thermalization, for these Heisenberg models with the non-commutative charges, there have been experiments on that, like for the, small scale systems already.
Mm-hmm.
Right. So in principle, these can be utilized. Now, and the only sort of issue is about controllability of the mu's, so the chemical potentials.
Mm-hmm.
Right. So these it needs to be controlled quite well, right, as you go about your gradient ascent
I
steps.
see.
So, and I think the next stage is to think about if there is, a continuous time way of directly doing that, right, rather than this hybrid kind of classical, quantum format. But certainly something that, I can't remember if I told Mike this already, but we have the classical software that we're
Mm,
developing.
I see.
So I want to put that like in there. And so
Okay.
when we have, because this is actually also a classical algorithm,
Mm-hmm.
right? So typically when, people think about semi-definite um, optimization, you have programs like the MMW. It's the same as Mark's initials.
Mm-hmm.
So um, multiplicative weights, a type of algorithm where you also have, Gibbs states, and this is why people are proposing, why quantum, Gibbs states are actually important.
Mm-hmm.
But no motivation was ever really given for why why thermal states, right? So
I see.
so whereas here you see the thermodynamical, background to that, and classically people use this. I'm talking about, classical algorithms of semi-definite optimization. So this is
Mm-hmm.
also yeah, like an alternative classical or algorithm, which you can put then in the software, for example.
I see.
And yeah, so but I'm not clear on sort of in terms of complexity type of advantages. So I am hoping for a more, physically motivated implementation. So for example, like, having, a system where you thermalize to some mu and then doing something else to your system, to change your mu kind of directly. And I think that's something that'd be more natural,
Okay,
for these
thank you.
problems. But
Yeah,
we haven't done it.
yeah, okay. Yeah, thank you.
I'll
Yeah,
chime in with a remark for Shin's question. So regarding simulation on quantum computers, the the code that we developed was led by Michele Minervini, who's on the call, and
Mhm.
we made that available with our archive post. And that was written for the simulations of the, maybe Ned, if you could advance the slide 30.
Yeah.
That was written for IBM Qiskit. And
I see.
so we have been working, Michele and I have been working with a master's student this semester in an attempt to get these to do some simulations on an actual quantum computer to see what one could observe right now. But that's in progress, and so we'll see how we do.
Okay, cool. And yeah, by the way, for Nana, your comment on the format of discuss session, Mark invented this. I think it's to invent this idea to simulate what happens during the coffee break of an in-person event.
Well,
Like
part
art
of it
studio.
is I realized that as you see, I have all kinds of questions, and there was not enough time between speakers to ask all the questions that I wanted to ask, and so I suggested that we do this. Not only,
It's a great idea, Mark. I just thought it would be more like a free thing rather than like per speaker. But yeah,
yeah, well, unlike a
struck.
coffee break, we're all like gathered around the same coffee table right now, and so we have to structure it in some way. As we're an actual coffee break, you can kind of break off, and we thought the breakout rooms would be a bit too complicated to organize.
Okay, yeah. So we just continue, yeah, due to time limit. So we just continue to the last speaker, Dhrumil. Any more questions for Dhrumil?
So I have a comment. Thanks for doing such a good job, Dhrumil. At the end,
Yeah.
you mentioned that there's not work on barren plateaus for QBMs, but there is the paper of Nathan Wiebe, who spoke on the first day, right? He has this paper, Entanglement-Induced Barren Plateaus, and they had certain assumptions like Hamiltonian, the QBMs with visible and hidden units, and they had a certain assumption of a random Hamiltonian, but you know, so we are aware of that, and under that model, if there's too many hidden units, then you do encounter a barren plateau. For
Yeah.
particular, like when you're trying to consider the ground state energy problem.
Yes.
Um,
Yeah, I should have said like because my talk was fully focused on the fully visible QBMs.
yeah,
Yeah, so for that I think it's not known yet. So
that's right. And the talk last night and in the US and yesterday morning by Eric Anschwitz was very interesting in this regard. It seems like he has a number of tools that could be used to address this problem and, possibly produce some analytical proofs. But I would certainly need to understand his work a lot better to be able to try to contribute there.
yeah, like if we can somehow remove the second order, which is a Fisher information calculation, and replace it with something smarter, I think yeah, that's very interesting. And yeah, because I think that's a bottleneck for now.
Mhm.
Yeah.
Okay, good. Any more questions for Dhrumil?
I've got a very quick question for Dhrumil. So, in the previous studies, I was trying to optimize to optimize the Gibbs state. So I have done some experiments. So instead of the Baron-Platos issue, I just realized that in many cases, in particular for the VQE loss function, I found that it might have no Baron-Platos issues for optimize the QBM, but it can have something like a very dense local minima near the minimizer point. So I was guessing that I think there is no currently a theoretical guarantees for that. And do you have any argument for it?
Yeah, I mean, so in the literature, at least in the, I don't know anything like people have researched in the QBM about this, like how to escape local minimas or saddle points using second order optimization. But at least in the classical optimization literature, people have looked into that and they have come up with some kind of assumptions. I have to recall. If those assumptions hold for your cost function, then you can probably say something about like that if you use a natural gradient or any other gradient optimizer, you can escape from the local optimal points. But like for most of the most of the loss functions, those assumptions might not hold. So yeah, we might like be stuck at the local minima, and we cannot say anything else.
Right. Thanks.
Yeah.
Okay, good. I think time it is a bit over time, and I think Mark, maybe you give the closing.
Oh, sure.
Yeah.
Thanks to all of our speakers for today. That was really interesting for logging on. We have one more session in roughly 9 hours for our
Yes.
workshop. And yeah, it was really good. It seems like, let's see what happens during the next year, but it seems like there's enough interest in this event where we could consider it again.
Yeah, sure. Cool.
So, all right. Well, everyone have a good rest or a good day.
Yeah. Okay. See you.
Okay.
Mm.
All right.
Yeah.
Yeah.
See you.
Bye.
Bye.